So you think of like, oh, I push the key and that's on, and then you release the key and it's off. But what's actually happening is that the key is oscillating a bit up and down. There's just a window of a couple microseconds where the key goes on, off, on, off, on, off, on, off, before it stabilizes again in the off state. These days, right, you go to like help for anything and it opens up a browser window, which takes a bit and then takes a while to like redirect you to the web page that maybe or maybe doesn't give you an explanation of what you're currently looking at. No, in Turbo Pascal, you move your cursor over a word in the thing, and even on the 286, it just pops up instantly and you're on the definition for the thing you're currently looking at. And it's actually well written. Yeah.
Maybe for the sake of completeness, we can start with this question,
yes,
which is like, how did you start programming? How did you get into all of this? And then we'll spiral from there.
And you can compare notes to see if I'm making all this stuff up as we go along, or if there's any consistency to my backstory.
Exactly, because
I'm just like deep cover mole, and I don't remember the details of my cover story.
It's just like make up you make a new cover
exactly.
story every time.
I just have a few bullet points and I just improv the rest, you know. Exactly. Like I have an uncle on my mom's side who works as a programmer, not anymore. He's now he's over 70 now, so he's retired for a couple of years now. But he worked as a programmer, and he's the one who taught me BASIC, the programming language. And like he had, what was that? Until well into the 90s, just the PC he had at home was an 8088, I think. Just real old school IBM PC with like dual floppy and whatever. But he taught me GW Basic on that thing. And like we had a PC at home. My dad had one in his office as well. And that in the early 90s was a 286. It's like a lot more luxurious. But still not exactly bleeding edge for the time. And so he taught me BASIC, and like he had some books. Like the one book that I originally learned this from, I don't think I have it anymore, will be here, but I don't think I have it here, is like Learn BASIC with a VIC-20. So I didn't have a VIC-20. He used to have one at some point. Like that wasn't around at the time. But that was how I learned programming from, with this book that's just teaching you how to program on the VIC-20. And like, since most basic programs, it's like you do really, really simple stuff, like whatever. Like toy example, I think that was one of the things in there was just like unit conversion from like Fahrenheit to Celsius and back. Like
still difficult for me.
You do like,
to be honest.
Yeah. In your head maybe, but I think in program you could write, right? Yeah. So it's like, it's just basically just one ratio and like a bias, and that's all you do. So that kind of stuff, where like 5 or 6 line basic program starts with an input statement and like read this value, and then you do the formula and print out the result. That's the kind of stuff I learned to program with. And then once you realized that I was enjoying this, like, and I was into that, so like I'm a bit too young to have grown up with a home computer era. If you're on a C64 or something like that, you start up the machine and you're in a BASIC interpreter. Or it wouldn't be a C64 for me. My grandpa used to have an Amstrad CPC 664, which is also one. That's another one from that home computer era of like 64 kilobyte microcomputers. This one is the 80, not 6502 based, but it's like the same kind of vibe. And that was also a thing that was just standing in the corner with like an old, like green only, like monochrome CRT monitor, that I was just fascinated by this device that was standing there and was playing around with that when I was at my grandparents, and my uncle, who was living with my grandparents at the time, also like explained to me like, oh, this is also using BASIC. So I played around with that as well, but I did more with GW BASIC at home because that was the computer I had more direct access to.
If you would like to support this channel, you can become a member on Patreon. You will be granted access to a private Discord channel where you can chat with other supporters and guests of this show. For more details, check out my website at łuka.sh. Łukasz.
And once he realized that I was into this whole computer thing, and like, hey, like he's a programmer, he knows how this stuff works. So it's like, okay, like if you want to do something a bit more interesting and sophisticated, like let's give you like a better programming language. And he just got me for my birthday, I think, would have been like when I was like 7 or 8 or something, just a book about Turbo Pascal.
Nice.
Like the language and the environment. Turbo Pascal 6 that had a floppy with the actual program of like Turbo Pascal 6. So that was both the actual IDE and like the programming environment and like a book on how to use it. There was not actually like the package you would get from Borland. I don't know where he got that one from. It was just some separate like publisher had cut a deal with them or so. Like they had their own thing. It wasn't the official Turbo Pascal manual, but it had an authorized copy of Turbo Pascal, and that's how I learned quote unquote real programming with. And that might have come up in other interviews. I've seen some of the ones he did. I don't know if, like how many. It's just a generational thing, right? Like the ones who are a bit older than me grew up mainly on the 8-bit home computers. The ones much younger than me actually don't know what they did, what that would be the first language. But like around the time when I learned programming, which was early 90s, Turbo Pascal was for sure the sweet spot. Because it was just great. Like it's a compiler, like very, very simple, like basically non-optimizing one-pass compiler, but it's better than an interpreter, which was what BASIC was. And so that was a very, very cool environment to get started with. Since like if you've used the IDE, like it's hard to explain now. It was a compiler. If you've used something like Turbo C or so from around the same time, or Microsoft C or any of the other compilers, all the compiled languages, like compiling stuff just took ages. It was really, really slow. Like people talk about how C++ is slow to compile now. It was so much worse then. Like they were much shorter programs, but you had machines that had very little memory, were of course much slower. These compilers barely optimized at all. Like the kind of optimization which is like, oh, they can turn x times 2 into a bit shift. Like that's the level of optimization they got. They didn't really register allocate on x86, 16-bit x86. You have essentially like 3 or 4 usable registers that you can keep values in that are not more or less special purpose. Because 16-bit has like all these restrictions on addressing modes and so on. So you would need a much more globally optimizing compiler than was really viable at the time to actually make good use of these registers anyway. So they basically didn't. Like it's just like, oh, like 2 of these registers can be used as pointers. It needs to be BX or BP or SI or DI, but these also have special rules and blah, blah, blah. It's just it's a complicated mess. So like all these kinds of things meant that compilers weren't very good. And if you actually wanted like anything that was like an inner loop, you wanted to write an inline assembly, which like Turbo Pascal had great support for, or you used a standalone assembler. But like MASM and TASM at the time is like, to this day, I still haven't found an explanation of the MASM syntax. Like there's a manual for MASM, like a reference manual that goes, oh, like here's the syntax for this statement. But like the thing about the MASM and TASM manuals both, it was bizarre. They both assumed like, oh, you kind of know this assembly dialect directly already. And there's at no point is there like any introduction of like, okay, like here's basically the boilerplate you need to write to just get something that compiles correct, that assembles correctly. So because you need a bunch of like, oh, I need to declare a data segment and a code segment and blah, blah, blah. So there's like 20, 30 lines of boilerplate you need to write in an assembly file. Like half the syntax isn't explained. Like, oh, you need to get like the offset of a variable to put as an address somewhere. Like, what's the syntax for that? And there's a glossary where like, if you already know the keyword, you can look up the page where it's explained. But like, if you're like, okay, I want to reference the address of something, how do I do this? And the answer in MASM is like, sometimes you just write the name of the variable and it just puts the dereference for you. And sometimes you need to write keywords offset off something. And that's just something you need to know that's not properly explained. So like I had this thing and like, okay, like there's in theory these professional assemblers, but like the docs for them are just kind of assuming that you already know or just like have something to copy and paste from. And this like even like years later, like we're in the 2010s now, where like at RAD I need to do something that deals with Windows a structured exception handling thing. Just, it was a thing where we had generated code, like in Pixelmatic, that needed to call into something to interact with Windows exception handling. And it because it was called from generated code, we didn't want the generated code to just have to set up a regular stack frame and so on. So we had stuff that was passed in certain registers, and I needed to write a small assembly chunk like, okay, take all the stuff that is currently in random registers, rewrite that into a stack frame that the Windows exception handling will understand, and then trigger the exception from there. And just, I had to write basically like a 20-line assembly program to that. The opcodes were clear, but it's like this was 64-bit x86 MASM that needed to interact with their safe exception handling macros, and it was a nightmare because the docs are still the same they were in the 90s, where like, okay, like in the 90s at least I had a bunch of projects that ship with like working MASM files.
You can copy paste
that you can just assemble and you can just copy and paste from. With 64-bit, like there are some differences. Good luck finding any working 64-bit x86 MASM file. They don't grow on trees. It's not something you find on GitHub. Like Microsoft has some in their kernel for Windows or so, but it's like that's not open source, and nobody uses 64-bit MASM. Like it's not nobody, but it's like that's not easy to find. So it's just a complete nightmare. And the docs don't tell you how this works. It's just like you try to assemble something, you get a cryptic error message about like, this section is missing. It's like, okay, I need to add this type of section, but it's supposed to be generated from a macro, and you don't know what the name of the macro is. So just go over the glossary again. It's just like, it's a nightmare. And then you're like, okay, like you think like, hey, this is Microsoft Macro Assembler, right? I can tell Visual C++ to output an assembly listing, and that should be valid MASM, right? So you take a random like short C program with just a stub function and tell it to generate assembly, and then try to assemble the resulting file, and that's when you find out that, oh, the thing that Visual C++ outputs as a MASM file does not actually assemble. Like they're not actually like syntactically valid MASM. It's just nobody has ever tried to actually assemble this. Like for 64-bit, it's just not something they interest. It's basically just debug output for compiler developers to look at the instructions, and the instructions are correct, but it's not something that like has ever been meant to be assembled. So like it's not easy to just get a working file. Anyway, that's all long-winded explanation. So like assemblers, anything like that's about the state of like how these tools are documented. Everything is slow in the 90s. The docs are patchy. It's just like kind of assumes that you already sort of know how this works or know how to deal with it. And then in that environment, like it's DOS, it's command line. You have all these cryptic, if you're a 7-year-old, like 2 or 3 letter commands that do things that are derived from CPM, which is copying from VMS, which is like all these operating systems that you also haven't heard about, has concepts like, derived letters that are foreign. None of this is explained. When it is explained, half of it is in English, which as a 7-year-old, of course, in Germany, you do not speak. So it's like everything is just weird, and suddenly you get Turbo Pascal. And it's like this program that you start, and it actually has like localization, and has online help, and you can just
nice.
You just type in a program. Like there's like a tutorial you can have F1 that tells you like, okay, here's how you write a program. I also had the book that tells me how to write a program, and you just in the text editor, you move your cursor over any word, hit F1, and it just instantly, and I do mean instant. It's not like later on where like, you go to these days, right? You go to like help for anything, and it opens up a browser window, which takes a bit, and then takes a while to like redirect you to the web page that maybe doesn't give you an explanation of what you're currently looking at. No, in Turbo Pascal, you move your cursor over a word in the thing, and even on the 286, it just pops up instantly, and you're on the definition for the thing you're currently looking at, and it's actually well written. So that was just complete game changer. Like Turbo Pascal was awesome. The code generation, as I said, was not good, but you had inline assembly, and you had source code for a bunch of library stuff, which also used some inline assembly and whatever. So you had example code to look at that used inline ASM. And like x86 assembly, especially 16-bit, is not that complicated. Like it can't do very much. So you sort of pick up the basics of like, okay, I guess this is this is that. And you just have some understanding, like Pascal is a simple language. You have an IDE. This comes with a bunch of libraries that are not super sophisticated, but everything that's there works, is well documented. You have like an understanding, okay, the next step for if you want to do this thing is like, there's like random things, like for example, like if you want to do stuff with DOS, there's these random interrupt calls. And they're like, there's something to do with interrupts. And like, okay, I need to know like whatever DOS, like file open and so on are int 21 hex, whatever that is. And that's something like you don't know what that is, but it's like you file it in your mind as something for later. Or if you want to set your video mode, that's also like a software interrupt, and you do interrupt 10 hex to talk to the BIOS, which sets the video mode for you. And you file that in your brain, and eventually like, so you have these things like, oh, there's other books or other things I can look up like for PC. If I'm on a PC, like how do I do this kind of low level thing? How do I that kind of low level thing? And like, if you look at a technical, like there's publishers, like in Germany, there was a big publisher at the time. I don't know if they're still around, called Databäcker. That just did like technical books like on all kinds of computers, especially like home computers. And they just have a book about pretty much anything, right? There's something there for anybody. Like if you want to know how like program, like how does my floppy drive controller work? Like you don't know that, but they have that. There's a book called PC Internals. That's like, here's how you deal with a video card. Here's how to deal with floppy. Here's how to deal with hard drive. Like, here's how all of these work. Like, there's supports you poke values into. That's the protocol they speak. It's all there if you want it. So it was like at the same time very, very bare bones, but it was just, it happened to be because 16-bit, like you couldn't put that much code in a program. Like, initially, the early Turbo Pascal versions just produced .com files in DOS, which means you had a 64K limit for like entire program plus initialized data. You could allocate memory after that, but the basic program and like all the global data had to fit into 64K. So everything was originally like, at the time I did it with, which was Turbo Pascal 6. They were generating .exe files, which could be larger and could use multiple segments internally. So that was a bit lifted. You still had a 64K limit on all global data, and everything else had to be in the heap. But like you could at least have more code. But like everything was still evolved from that time when you really, really had tight size limits on everything. So all the libraries were small. So like you have a library like uses CRT, I think, in Turbo Pascal that had to do with video output, which had like a couple functions. Like there's one to go into text mode. There's one to go into like one of three graphics modes that this library supported. And like in text modes, there's like move the cursor, like write text at this kind of thing, change the color, that kind of level of abstraction. And likewise, there was like, for graphics, you had like a special library called BGI that let you draw lines and circles and stuff. So like basic graphics algorithms, some pot pixel, and just work from there. So all these libraries were very, very simple. But that was nice because a lot of it came with source code, and you could just look at like, how does this actually work? You didn't have source code for all the libraries, but the entire UI framework that the editor itself was written in was something called TurboVision, which was this like pull down menus. You had dialog boxes and all in a text mode user interface. It was this whole like OOP, like windowing toolkit kind of thing. It's like, this thing like can do pop-up windows in text mode, and you had full source code for that, which was a fairly complicated thing at the time. And you could say, like this thing has a bit more organization, and you had some examples of like how a more complicated program looks, right? Because as I said, like you initially bootstrap this, like you're writing like programs that fit basically in 1 or 2 pages of screen real estate, like read a couple of inputs, do a computation, write the outputs. That's what you started with. And then it's like, this TurboVision thing is like a program that has user interaction and like has some abstraction for what's on the screen, like has like a notion of like what rectangles are, so it's using structs for that, and it has a notion of an event loop. So like that's all kind of things that are not natural things to think of when you're learning programming, but suddenly you have this window into like, oh, this is a more substantial thing that I know is useful, because the Turbo Pascal IDE itself in later versions, and like I think Turbo Pascal 6 was still a different one, but by Turbo Pascal 7 they had rewritten the entire IDE to also use these same libraries they were shipping. So you knew like, oh no, this is legit, like this is a real thing that they themselves are using, and it was sort of a window like this is how a more complicated program is designed, this is how that works. So you got like, it was very, very cool, where on the one side, you had these very, very simple libraries that didn't really do much. But then you, at the same time, you had some of these libraries like the Turbo Vision thing that like, oh, no, there's an abstraction here for some kind of device independence where like, yes, it could do this in the usual like VGA 80 by 25 or 80 by 50 text modes, but it also like could support at the same time, and like on a second screen on a Hercules monitor, you could have like a grayscale thing driven from the same thing, and it was written to support all of that. And so I was like, oh, like this is like, there's some substance here. And that was very, very cool. And like, I think I spent the next few years just like looking at that stuff and just basically learning more about how you could possibly do a larger program that did something more interesting with that. And then I also got really, really interested in just like anything graphics was cool, because it's just nice to just put stuff on the screen and see it move. It's just very immediate. And the way that worked out, like there wasn't a nice abstraction to get into what's probably the nicest graphics mode to use on a VGA graphics card, which was like what the BIOS calls mode 13 hex. That's 320 by 200 pixels, 70 hertz refresh rate, which is the VGA special, and 256 colors, 1 byte per pixel. So you had, at a certain location in memory, like segment hex A000 in the DOS memory map, you just have 64K, and I do mean 64 decimal kilobytes, because 320 by 200 is exactly 64,000. So 64,000 bytes of just like top left to bottom right, just pixels, 1 byte per pixel. And that was just a very, very nice video mode to be doing graphics programming in. There was no real library support for that graphics mode. There was other stuff, like all the line drawing and so on was intended for higher res modes with like 16 colors and so on, which I wasn't as interested in, because all the games were using the 320 by 200, 256 color mode. And that was also the one where like, when you're doing like the 16-bit color modes, that was a lot more different logistics, because the way the whole thing worked is like the video memory in those modes is organized the same way it would be in, say, an Amiga, where it's stored by bit planes. So you have one block of bytes that's like, this is bit 0 of the color index. And there's a whole separate region that you need to access in a different way. You needed to poke in some ports to change the mapping to get the bit plane, like this is bit 1 of the color index. So if you wanted to change the colors for a pixel, you needed to basically do it 4 times. Like write bit 0 of the index into the bit plane for bit 0, bit 1 of the index into the bit plane for bit 1, and so on. You need to do that multiple times. And like the 16-bit modes, not 16-bit, the 16 color modes always needed you to do the futzing with these bit planes, and it was kind of a production. But the 256 color mode, 1 byte per pixel, it was the easiest thing in the world to use. So the standard thing you would do in Turbo Pascal, just like basically, 2 lines of inline assembly at the start. You just did ASM, move AX, 13 hex int 10H, which like that's calling the right thing to just like, that's turns out like setting the high half of AX to 0 is the set video mode function.
Okay.
So you just set the AX register to like, okay, operation 0 mode that went in the low half of AX of 13 hex. So it's like one instruction to just set both of that up, int 10 hex, and then you're in the graphics mode. So end assembly, that was all the assembly you need. And after that, you can just start poking into memory at the right location and do animated graphics. So that was
How
very, very
the
cool.
hell you remember all of that?
I have used that semi-recently.
Okay.
Specifically, that was in 2013.
That's recently.
I had,
But okay.
that's why I said semi-recently, right? It's like the point I'm trying to make. This is not 40 or not 40. It's like 35 years ago for me. It's like 10 years ago for me, which is different time frame. Specifically, this was. We might get to this later. Like I was contracting for Valve at the time while they were starting their AR/VR efforts, and one thing we were trying to do was some latency measurement kind of thing. And the issue with that is, how do you bootstrap this process? Because initially you're on a Windows machine, like everything you can interact with on this machine, right? You have video output, you have keyboard, you have mouse, like any input device, like you can potentially, like we had hardware guys, you can potentially poke something into the serial port, like just a couple of resistors, wire up a signal there, just a switch or something like that. We actually had one of those. And just like some of these are lower latency than others. And we need to figure out like how fast can we possibly get the input latency from like event like on the input device happens to something happens on the screen. And the issue is, if you're on Windows and you have a bunch of drivers stacked in between you, all that is abstracted away, right? You can talk to the serial port, but you open a device file that will eventually give you a whole byte, and you have no idea what the latency of that stack is either. So the question becomes, if I'm trying to figure out what the lowest latency path on this machine is, like I have no idea what can even potentially be fast. Because if I have a keyboard at this day and age, it's going to be a USB keyboard. And like, so there's not a direct thing where like I push a key on the keyboard and like the keyboard hardware has to, like, there's a grid of wires in there, and it puts, like, it does a scan where, like, puts a voltage on each row in turn. And when you hit a key, like, that connects that row with a column. And what a keyboard controller does is, like, it puts voltages, like, through these rows in turn and scans them and sees if anything arrives, like, at the corresponding columns. That's how keyboard works. That's the matrix thing. And by the intersection of which row you put the voltage on and which column the current arrives at, or the voltage arrives at, you can tell, like, okay, somebody must have pushed this key because at each row column intersection is exactly one key. But so there's a scan process where, like, there's something, like some controller there that needs to initiate on a keyboard periodically, like needs to step through these rows, like, okay, this row, then this row, then this row, then this row, and needs to figure out, is there actually a voltage? And then because of the way keyboard switches work, like it's a mechanical switch, but it turns out, like, at any kind of time scale, if you scan things like fast enough, like this is just a weird thing about the world in general. Like we think of like, oh, I put a thing on a table and then it sits flat. And if you look at that with a high-speed camera, that's never what actually happens. Because it's all springy bullshit, right? It's like mass spring systems. Like, we're just used to thinking of it. It's like, oh, you put something on a table, it sits flat. And like, you're sort of aware, for example, that if you're on like slightly soft ground, that when you just jump on something, the ground actually shakes a bit. You do notice it when, like, whatever, like a heavy like horse carriage or something goes by. You notice that the earth is slightly shaking whenever the hooves hit the ground. And it's just like, yeah, everything is like that all the time. Like, everything is vibrating all the time. And specifically, when you hit a key mechanically, there's just a mechanical switch that's either in the on or off state. But there's no perfectly sharp transition from on to off. So you think of like, oh, I push the key and that's on, and then you release the key and it's off. But what's actually happening is that the key is oscillating a bit up and down.
Okay.
So there's just a window of a couple microseconds where the key goes on, off, on, off, on, off, on, off, before it stabilizes again in the off state. Because you just, like, it's a spring, right? There's a physical spring there that pushes the key back up, and it just oscillates after it, like, because it hits like the thing at the top, and then it bounces, and then it hits it again, and it bounces. And you just need to wait for that to stabilize. So what actually happens is not just like, oh, okay, like there's a scan that needs to happen, which happens a couple. I'll get into the frequency of that later. It happens a couple times a second. And then after that, you see like, oh, this voltage thing happens, but it also just vibrates there. So just normal mechanical keyboards need to do this thing called debouncing, which is just because, and it's not just the mechanical swing, there's also electrical thing, where like also even like an electrical switch, when you go from like, oh, there's a current flowing to just, I turn this off, like electrically, like I just sever the connection and it instantly stops flowing is not how it works. If you've ever seen like there's videos on YouTube, like an electrical substation, there's these high voltage switches. There's videos of these switches opening, and what's happening if you have a real high voltage switch that there's actual current running over that you open. These big mechanical devices, and you see this thing slowly like turn, and while this is going, there's like a big electrical arc and and eventually it cuts off, but it takes a couple seconds. This kind of thing, that's how your light switch works. There's a tiny bit of arcing every time because there's some momentum to these electrons moving and they don't want to just stop. So they just keep flowing even if you interrupt the connection and you have a bit of arcing. So like everything in the system resists like your desire to have a perfectly sharp key press, right? And so you do, what happens, why I'm explaining this, is that you do some post-processing either on the keyboard or itself or in the keyboard controller. Like, oh, the voltages I'm getting out of here are just kind of a bouncy thing. And you just know this happens, right? So you're like, oh, like I press the key down and you know the key press is clean, but you know the key releases are kind of wonky. Where like it releases, then it unreleases, then it releases again, then it unreleases. You just know that every time there's a key up event where somebody just releases the key, there's gonna be like a weird time after you get the first key up where, oh, the key's moving up again, where it's going to be just kind of like pretending like you're toggling it all the time. And so there's a thing called debouncing that happens where you just, after you notice like, oh, there's a key up event, there's just a certain time interval where you just ignore all the readings. You can't just, like, this is microsecond scale. It's like 10 or 15 microseconds, but you just have to know, like, there's just garbage that happens and we ignore that. And there's just a long interval where you just do this. And like, I am aware of all these things intimately now because, of course, what we did, we wanted a low latency input. And you do some experiments and like at some point you realize, okay, we can't actually do this in Windows. So I'm like, well, this is a PC. I know just like literally just take a CD ISO image, burn a CD, which at that point I hadn't done in quite some time, with a FreeDOS image to boot from it. And just like, okay, like put like some assembler on there and just write a small program because like I still like, I remember half the ports I need to do to like actually talk to the hardware, half of which is emulated now, but it's still emulated in hardware usually. It's not a software emulation. And even if it is a software emulation, it's like a lot more predictable latency than what you would get on a multitasking operating system. So it's like, okay, boot this thing into DOS, poke the ports, and see how fast latency we can get. And the thing we ultimately had was just a thing where we had this hardwired mechanical switch. And then I need to go one further. The first thing we built was like, okay, we need to get the computer out of the loop because we don't know like how good any of this can get. So what we had was just, we have a program that's just generating a video signal and just took a VGA cable, like old school VGA cable, like the analog ones. You can't really get those anymore. Nobody uses them anymore. Like the 15 pin, I think, DIN ones. So it's like 3 rows of pins. And that has the advantage. There's a bunch of sync signals there, but it's generating a visible signal. And like there's 3 wires, one for red, one for green, one for blue, which is very, very nice. And just had one of the hardware guys, okay, like open the installation on that cable, get out the wire that's, I think, the blue signal, just physically cut that, splice in a mechanical switch that allows us to like disconnect that wire. So we just set the thing just we make an entire blue screen. It's just blue. And we have a mechanical switch that we can toggle that'll like physically interrupt the connection, and that should be basically zero latency, right? So we have a monitor, and this was an LCD screen still. If you did this on a CRT, like this is also all analog. But the first question was like, we don't know what the latency for like an LCD screen is because some processing happens. So we take an LCD screen that eats that VGA signal, and we have this physical mechanical switch that we know, like, no, the instant we toggle the switch, the voltage changes because there's no other physical mechanism here, right? This has to change right now. Like, we're directly interrupting this current. So we have an LCD screen that is just solid color blue displaying. That's this program we wrote, which is trivial. And this mechanical switch, we have one, like Canon did some like consumer high-end DSLR cameras, or was it not DSLR? They did a bunch of cameras that had like a high-speed recording mode where you could record at like, I think up to 1200 FPS on like a tiny, tiny window of the sensor. So we could do like a homemade like high-speed photography, carefully framed a shot where like we have the screen in the background showing this what used to be solid blue, and the switch which lets us interrupt that solid blue and turn it into black instantaneously, and then film us like with both of these in frame, like hitting the button, releasing the button, hitting the button, releasing the button. And of course, what happens is that at some point, like when you push that button or release the button, like you get a stripe of black on the screen. And the position of that is wherever the video card currently is in scanning out the frame. And so it's not always going to be in the region of the monitor that you actually have on your shop, but like you film that for a couple seconds and like you will get some of these. And what you can now do to figure out the latency of the monitor, because you have a video of you physically pushing the button, and you can see in the high-speed video how many frames, you can just frame count, how many frames until it turns black. And what you find out is that there's basically zero latency. Like there's a couple microseconds maybe, but like if you were feeding an LCD screen at that time, at least the ones we used, like you can like the instant that signal goes to zero, there's maybe some scalar there. It's maybe buffering like a line's worth of data or something. But if you look up how many scan lines in VGA modes get delivered, it's like a line frequency of about 15 kilohertz. So 15,000 scan lines delivered per second in like the standard VGA modes. And that's pretty high frequency. That's microsecond latency. So at the frame rate we were filming this, which was like millisecond scale, it was instant. So like, okay. So at least like the monitor might be doing some bilinear filtering, but it's not introducing frames worth of latency. It doesn't have the memory for that, or at least it doesn't have to. Nowadays, monitors do, because TVs support all this motion interpolation stuff, right? So nowadays, you need to be careful. Nowadays, monitor has the physical memory to introduce multiple frames of latency, but at the time, it didn't. So, or at least not the monitors we were using. And we could see, okay, if we instantly change the signal, pretty much instantly, we can get the signal on the monitor to change. So that's our baseline. And we know at least the monitor won't screw us over. Like the monitor can run at close to zero latency, which is like good. Now we can start figuring out which input device works. Bunch of experiments later, it's like, okay, we write a program. And that was where the FreeDOS thing came on, to do this like with an actual program running the show, because of course we want to do a low latency thing on a PC, and we need to be doing that from our program. It's nice to see like we can mechanically like basically like hotwire the signal, but that doesn't help us. Like we need to generate this from the computer. We just wanted to have a baseline for how low latency can get. So the next thing we do is we have a program that's pulling, like I think initially we tried the keyboard controller, which of course like the old school keyboard thing is now emulated. Like, because the actual keyboard you're connecting is USB, and there's a program in the BIOS that if you try to pretend it's like an 80s era, like old school keyboard, and like poke the ports to do that, there's just a program that's running that translates USB events into whatever you would get. It's just a software emulation that the BIOS does, because whatever bootloader your OS has might have something like a boot menu that doesn't know how to speak USB because it doesn't have a USB stack booted. And you also might boot into something like, hey, FreeDOS, which doesn't know anything about USB. So there's a weird software emulation layer in your BIOS that actually, like, whenever you try to talk to the hardware ports that would ordinarily be like an old school like PC keyboard, it actually goes to a software handler that just pretends it's a PC keyboard, gives you the results back. So there's some emulation running, and we learned very quickly, like, oh no, this USB stack is terrible, and it has about 50 milliseconds of latency. And part of that is because turns out typical keyboards, like their scan frequency, like how often they go through this procedure of like scanning the rows, the default used to be 50 times a second. So like even like 60 hertz tapping, like that you might do in a game, right? Like you can't actually resolve on a default keyboard with the default USB scan rate. It just won't work because it's not scanned often enough. These days you have gamer keyboards because like after this whole VR thing, like this whole latency thing became a thing that gamers were suddenly aware that they should be worried about. And now you get like mice that advertise scan frequencies of like 1,000 hertz and plus, and keyboards that have 1,000 hertz and plus. But at the time, the default scan rate for keyboards was 50 hertz, and I think mice were initially even lower. And then for a good while, they scanned by default, I think, at 125 hertz. Like I remember, like in the Windows 2000 era, that was a registry setting or something you could set to up the USB hit scan rate from like, I think, something like 30 hertz to like 125, which on a 60 hertz monitor meant like suddenly like the mouse pointer was actually smooth. And that was just like this weird trick kind of thing you had to enable at the time because it was not the default. That changed soon after. But like, anyway, I'm getting tangents upon tangents. But the whole point is I wrote the small DOS program. Like we knew keyboard doesn't work for this. Whatever keyboard stack we have in this DOS emulation is actually garbage. We can't do a key press. But we did learn like, oh, the serial port thing seems to be actually pretty much a regular serial port. So the next thing we did, like we still have the weird spliced cable with the analog switch. And this time, we just a resistor wired up to like the ground or VCC or so on the cable on the serial port, and we can set the data line of the serial cable, again with a mechanical switch. And that is something you can read easily. So that is or was it parallel port? One of the two. It was something like that, which was fairly easy to probe. And it turned out that had low latency. So that then on Windows became like, okay, can we, because ultimately we wanted to run this on Windows, and we had this small program that did this on DOS, poke the port, see what the value is, put something on the screen, which we actually did was change the color registers. There's just the way this works in VGA is that you have like a color table where like color 0 is usually black, color 1 would be something like blue, like dark blue, and you can change the color table entries. And the interesting thing there is like if you have a background color set for the whole screen, usually, and that might be something like black, and then you change the color table entry for black, and if you do that, it turns out it responds pretty much instantaneously. So you don't need to know where on the screen like your video card is currently displaying. If you're like actually changing something in video RAM, you need to know which location to change, because like if you have a 60 hertz frame, that means it takes 1/60th of a second roughly to transfer that entire frame from the video card to the display, right? So like the top of your screen is technically, like if you think about when the signal is transferred, the top of the screen is about 16 milliseconds earlier than the bottom of the screen in terms of when events happen, because like that's just like it takes about 16 milliseconds, a bit less because there's blanking intervals, to transfer the contents of the image. So if you're changing anything in video RAM, you need to know which part of the thing to change, because wherever the video card is currently outputting, which is not something you generally know, like there is a location on the screen that will be displayed very soon that you could in theory change right now, and that will then show up instantly, but you don't know where that position is. It keeps scanning like this, and at some point like there is like wherever you are currently, like there's a position that the scan out is currently at, And you could, in principle, like change something right in front of it and it would show up immediately, but you don't know where that is. So instead, we just set it to a mode where it's just all displaying a solid color, and that color is black, and we can't change the color table entry for what this black color actually displays. And because every pixel that we're displaying is black, it'll just show up instantly the moment we change that color table entry, no matter where we are on the screen. And we don't need to know where the video card is currently displaying, which is a whole different can of worms. So that was the next day we did. Just like wire up the serial port cable to this small program that just pulls this one bit, puts the like, if it's set this color to whatever, 255, otherwise set it to 0. Actually has to be 63 because 6-bit table entries, doesn't matter. You do that and just have a program that in a tight loop does this, and it turns out like, yes, you can transfer this bit from the serial port into the VGA color table and it still has low latency. It's like, okay, so now we have progress because now we have an input device that is connected to a serial port, which is something we can potentially read on Windows. That's a regular device. We have a program reading whatever gets written to the serial port, turning it into something that shows up on the display device, which is also something we have an interface for on Windows. And it shows up on the screen, and we can verify with our high-speed camera. We push the button, and it still lights up within the same frame. So it's basically instant, right? Within at least less than a millisecond latency usually, which is what we wanted. So long story short, the reason I had some DOS programming in the 2010s was just because, like, okay, that's the closest. Like, you can also do this fully bare metal, don't even use an OS at all. But it's like, that's kind of a pain in the neck, right? At least on DOS is bare bones, but it's still an environment where you can iterate. You can just have a text editor. Like, you can write, like, I don't even remember, like, he had like USB stick or so that was also mounted that he could write to via BIOS emulation again. So we had an environment we could run a text editor on, like you could assemble programs on and iterate to just do these small programs that just poke like a byte from A to B, just to have like an environment where we know, okay, there's as little between like the actual inputs and like the video output as we can reasonably get. I mean, in theory, you can write your own complete or operating system and so on, which is something I have tried in the 90s, but that's a whole different, like, that's a lot more complexity than just booting into DOS and just doing the thing. And so that was just our bootstrap for latency things. And then, like, of course, once we knew, like, okay, we have verified, like, we know a path that works, and then we do the same on Windows. Try to do that through the regular Windows serial interface that uses device files. Turns out that doesn't work. But then we find out, oh, there's this weird driver that's not supposed to exist because it completely violates like all like separation of privilege thing. There was a driver you could get that had gotten signed somehow for x86 64-bit that just let any user space program like poke in an x86 IO ports, which is supposed to be a privileged operation. And it just gave you, like, just in the privilege tables, just said, like, okay, you're allowed to do this now. Which is not, like, that driver, like, how that got signed, that's not supposed to be allowed. But that driver did exist, imp out 64.dll or something, and, like, some weird pieces of hardware actually, like, shipped drivers that use this thing, which they're definitely not supposed to do. And it turned into a whole thing where that person has to publicly disown that driver and apologize for writing it, blah, 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 because it's like, it's a weird thing. You can look up, there's a whole story. Because, of course, like once this thing exists, people are going to use it to actually ship software. But it was exactly what we needed for our testing. Because we just do the serial port I.O. that's just very low latency, gives us the raw bytes. Didn't need a driver in the loop when we could just do it from our code. And now we have an input that we know is microsecond scale latency, which is what we wanted. And then we still have the Windows display stack, but once you have like one part of this, you could also use that serial port as an output. So you could also just generate like, or use a different serial port, which is also what we did. just put in a separate card for the second COM port, and then so you had some way to get low latency data in and out that you could use to bootstrap other latency measurements. And then suddenly from there, okay, how low can we get video latency on Windows? Turns out if you time everything right, if you know what to do, pretty good. I mean, there's still the whole thing where I said, this is slightly different now with DisplayPort, but VGA, DVI signal, as said, scanning out of frame takes 1/60th of a second roughly, if you're at 60 Hertz. That's how it's arranged. Because physically, there's some amount of data that needs to be transferred, right? If you think, say, 1920 by 1080, that's about 2 million pixels. Each of these pixels is red, green, blue, 1 byte each. So that's 3 bytes per pixel times 2 million pixels is roughly 6 megabytes per frame. So if you do 1080p at 60 Hertz, that's 360 megabytes that needs to be transferred per second continuously, which is by today's standards, that's not as huge anymore as it seemed in 2010, but it's still a lot of data. That's, for example, that's a lot more than you can continuously transfer over something like gigabit Ethernet. 1 gigabit Ethernet tops out at a bit under 100 megabytes a second. Just that's how much payload you can actually get over there. So your video link, purely in terms of data that is transferred, especially if you use a high refresh rate mode, or high resolution 4K, that's a lot of data still. That's gigabytes a second. And that's in terms of power consumption also, that's one of the more power hungry things you do in terms of IO. Because you have a cable that needs to be at least a couple meters long that you're pumping gigabytes a second over. So this whole thing is that's a substantial amount of data that needs to get transferred. And that means there needs to be a fair amount of logic involved with that, right? If your video output has that much data that is just shoveled to the display every second, then unless you do something fancy, which turns out for power saving and so on, GPUs now also do. There's now a thing, especially for laptops, where basically the display also has a memory. And the GPU can say, oh, only this part of the screen actually changed, and only transfers the dirty rectangle that actually changed. And then there's some other provision where there's a mouse cursor. That used to be something where you physically drew the image of the mouse cursor onto the frame buffer. That used to be how it worked. The OS actually did that every frame. And then it turns out, especially if you if you want to do this at 60 Hertz, this is something that has to happen every single frame. And it kind of sucks. So this is not really a thing you do much anymore, but turns out modern display hardware still supports essentially sprites, on an Atari 800, just for the mouse cursor. You have 2 or 3 sprites, something usually, in the display hardware that can actually do even things like alpha blending, because mouse cursors can have alpha and have shadows, drop shadows. It's there's sprite hardware with alpha blending support that can be 2 or 3 layers of overlay of just a 32 by 32 or similar image just to show your mouse cursor. Because it gets composited into the image, the OS doesn't need to render it every time. Because it's lower latency that way and lower power. And now displays in the newer version of this with EDP, embedded DisplayPort, I believe, can also do this compositing. We're just saying there's this position that the mouse cursor needs to get drawn at, but I don't want to be resending the 32 by 32 whatever pixels every frame because they could potentially change. So it's no. We tell the display where the mouse cursor is at, and it can just composite it over. That's not required. There's always fallbacks, but it's if the display doesn't support that, well, we just have the hardware composite it and send it as part of the dirty rectangle every frame. And if the display doesn't support the dirty rectangle stuff, which not all displays do, because that means they need to have memory to store these 6 megabytes or whatever of data. That's memory that needs to be in that device somewhere. And not all displays have that or want that. So there's also cases where sometimes the GPU has to draw this. And then there's cases where what if the GPU doesn't support this? At this point, all GPUs do. It's just a standard thing. But conceivably, you can have a very old GPU that doesn't have the support. So there's also still a backup path in the OS where it actually renders the mouse cursor every frame. But this is like everywhere you go, you have these weird stacks. It's like, oh, like this is the new stuff we want to do because it's more power efficient. So for example, if I'm looking at a Word doc, right? I'm sending this image 60 times a second. There might be a blinking cursor, but otherwise the image does not change at all. Sometimes I move my mouse cursor, which, as I just explained, like we have a special purpose hack just for that. We just send it, here's where the mouse cursor is. That gets handled elsewhere. But otherwise, the image doesn't much change. And if you think about like a productivity use case where you have a laptop, like, oh, like somebody wants to write, like is on a flight or on a train ride or something and wants to write a Word doc. Like, just driving the screen, just sending these hundreds of megabytes a second, every single second continuously consumes a fair amount of power. And we don't need to do that if you're looking at a Word doc that is just the same thing every single frame. And for decades, we're like, yeah, we're not worrying about this. But because physically, just memory was too expensive to put it in the display. But these days, like a couple megabytes of memory is just not that expensive anymore. And we're just like, whatever. It's better than transferring it every time.
How do you know?
If you go to
how do you know this? Like, even if you work at this, at something that is related to this, you still need to like spend weeks researching and reading and understanding, and then I guess playing with it to make sure that sometimes it's weirdly documented, so you need to kind of play around with it so that you actually understand it. Like, I feel like you are talking about like 3 lifetimes worth of knowledge, packed into these. Like, how do you know that there's a backup for a backup for a backup for a goddamn cursor?
Oh, I was there. That's the answer to this particular question. Like, when I started programming, the mouse cursor was something you had to render manually. So a thing you would use to see a lot, because this was something like on DOS, the mouse drivers did. And the way they drew the mouse cursor, like you could turn on, just tell the mouse driver, like, please show a mouse cursor. You didn't have to render that yourself. But the way it did that was basically, it grabbed whatever pixels were under the mouse cursor, right? Then rendered the mouse cursor on top. And what happened, this was very visible to you as a programmer, because what happened when you animated like something below it, like while it was doing this, like the pixels it would write would have background from the previous frame. Because like there's no synchronization there. Like you have something in an interrupt handler going like, okay, it's time to paint the mouse cursor now, let me do that. And it does. And then it just does the save restore thing. And it has no idea what your program is doing. So suddenly, like, you get cases where there's weird garbage on the screen from what used to be below. And I just changed these pixels, but the driver overwrote it. So you became very aware, like, oh, I guess the mouse driver is something that needs to get painted, huh? And there's APIs to tell the mouse driver what you're doing. And like, oh, actually, like in this case, when you're animating, you might want to render the mouse cursor yourself for this exact reason. So you can do that. But this was something you're keenly aware of at the time, like, oh, yeah, I guess somebody has to render the mouse cursor, and how does this happen? So then you run something on Windows, and you're aware, like, okay, yeah, I guess the mouse cursor is something the OS needs to render. But that's why you have an OS, right? It's the whole point of an operating system is that you have a bunch of devices in your machine, and somebody needs to be in charge of managing access to these. Because there can be like, what an OS does is like lets you run multiple programs at once, at least if it's a multitasking operating system. And once you have multiple programs running, you need like, they can't all just be writing directly to the screen. They can't all just be pulling the mouse directly. That doesn't work. Because sometimes you want this app to have input focus and sometimes you want this app to have input focus, right? And if both of them like just read the raw mouse input data, then whenever I click both app things, I clicked in their window, and that doesn't work. So somebody needs to arbitrate access, and that's the same for a network, that's the same for disk, like that's why you have a file system. The point of a file system is just like, okay, like every app wants to access the disk in some way, but we need to like we literally need a system. Like we need a file system, and we need to like organize like some units of data because they can't all just start to the disk at offset 0. That doesn't work, right? They all stomp over each other. So we need to figure something out here. That's fundamentally the purpose of an operating system, is to control this kind of access to a shared resource. That's their main job. Historically speaking, these days you have all kinds of other stuff like stuff like, the user experience, which is like not along that same vein. Like that's a different thing that has a lot to do with user experience and not much with controlling access. But there's still a lot of classic OS-y things. And you can see all these things growing during the time like I started programming in the early 90s. And like you can see these capabilities shifting. So for example, when I started programming, it was on DOS and it was just single process. And everybody did just talk to the hardware directly. I mean, you could use the BIOS to set the video mode for you, like I explained, but you could also just poke in the registers directly. There was not much reason to do it that way, but you could. Sometimes you would also just set a video mode and then change some parameters. So for example, like the 320 by 200 mode, a common thing would be to like set it into that mode and then change some registers to put it into what's called mode X. Which like changed the timing a bit to 320 by 240, because the 320 by 200 had odd-shaped pixels; they were not square. 320 by it was a 4 by 3 screen, and like 320 by 200 is a 16 by 10 aspect ratio. But the CRT you're running on this on is a 4 by 3 ratio screen, so your pixels have an odd shape; they're squished. They're too, or not they're squished, they're too tall, right? So like if you draw a circle in that mode, it doesn't actually look like a circle. So people would change the timings of their video mode slightly to use, instead of the 640 by 400 pixel mode, use the timings for a 640 by 480 pixel mode, which made the pixels square. But now, I explained earlier, 320 by 200 is just under 64 actual kilobytes, right? It's 64,000 bytes. So you have 1.5 kilobytes left, and that's the end of the RAM you can access in the 64K window you have. 320 by 240 is more than 64K. So suddenly, if you do that, like VGAs actually had 256 kilobytes of RAM, not 64. But you need a way to access the other RAM. And there was a way to do that, but it was a lot less straightforward. And it required you to interact with some of the same hardware you dealt with the whole bit plane thing for 16 color modes. So that was more complicated. It did mean that you suddenly had enough memory that you could address, not just for what you were currently seeing. You had, as I said, 256 kilobytes, which even with a 320 by 240 meant you had enough RAM to actually double buffer the screen. So you had, like, whatever you're currently displaying, you can have a second copy on the screen that you're working on, and then you could page flip what you were showing at the time when you were actually done painting to that. And so suddenly you could tearing free animation. Whereas in the 320 by 200 mode, if you were using that, had a lot of it going for it, but you needed to be very careful when you updated the screen, because it was the same data that the GPU was reading from right now. And if you were not fast enough, you would see screen tearing. So anyway, all this stuff is so like you seeing, like if you're starting this in the 90s on a PC, you see these layers being put into place one by one, right? You're on DOS, everything is raw access to the hardware. Then at some point you grudgingly use Windows 95, whatever. And that abstracts, like, okay, the screen, stuff like the mouse, the keyboard is now abstracted. Like the OS does things like Windows and input focus. And then later gives you an ability to like direct draw full screen. So you can still have a full screen video access if you're doing a game or something. But it's still done in a way where you can still task switch out of it, which sometimes even works, right? Like, because the app had to still do a lot of legwork there, and it did put the GPU into a page flipping mode. And so if the app, like, there were all kinds of weird interactions with the window manager in those days where all tabbing outside of a full screen app was a very, very dangerous proposition. It didn't really work right for most of the Windows 95 and Windows 2000 days because the app still had too much control. These days we don't have that because, like, no, now the OS is fully in charge. And basically, like, the way, like, even like a full screen mode works is like, there's still a thing where it ultimately, like, in certain cases lets the GPU display directly from whatever your app is rendering. But the way it works now is that there's an actual compositor in charge that's like, that knows how to render windows on top of each other and renders these with the GPU. And it just has a special path where it sees like, if you have a borderless window where the area of the window lines up exactly with the extents of the screen, I don't actually need to copy from the back buffer for that window onto whatever full screen buffer I have. I can just tell the GPU, just use the buffer in memory where the window data is and just display that on the screen. So that's now something in the window compositor, where normally like Windows, you render stuff into every window has its own buffer where the pixels go. And then there's the compositor is this program in the OS that goes like, okay, I have the contents for all the windows and I'm going to render them in the right order on top of each other, render the window borders and produce what actually goes on the screen, which adds a couple milliseconds and some extra latency.
Is this why? If you Alt tab from the borderless window, it's like extremely fast compared to the full screen window? If you have a game, you can set it to be full screen or borderless, and borderless is like instant, but full screen takes visible amount of time.
It's one of the reasons. Yes, there's some special cases there. Like, it turns out even actual full screen is now mostly borderless. Like the way it's implemented, but yes, there's just some kind of thing. It used to be, so in Windows 95, if you did this, games would actually use this whole page flipping thing where you have two screen buffers, right? One is the primary one, and one is the backup, and you keep toggling back and forth between them for smooth animation. What used to happen on Windows 95 in full screen mode was if you alt tapped, Windows had no idea which of these two buffers was the current one. And Windows itself would always just be rendering to the first one.
Okay.
So if you alt tap from a full screen mode gain, you'll literally at 50% odds that either you're currently on buffer 0, in which case after you alt tap, you see what Windows is doing, and you just like alt tap out of your game. You're still in the resolution you set, which if it's like 320 by 200, Windows at 320 by 200 is not a good experience, let me tell you. But it does technically work. But 50% odds it was currently on back buffer 1. And if you alt tap, you're still seeing the back buffer 1 that the game did. Windows now thinks it's in the foreground. You can't interact with it. You can't see it. And so you have to alt tap back blindly and try again. And again, 50% odds. So you basically had to do that a couple times in a full screen mode. And like sometimes it would work and sometimes it would not. And also sometimes, often actually, the games would just crash in full screen mode if you all tapped away from them, because nobody actually tested that path and something went wrong when you did that.
Okay.
So that's why we now have the compositor, where at some point Windows went like, no, we can't give you direct access to the graphics hardware. We're going to screw this up. So the way it now works is the exact opposite. We're like, no, Windows is always in charge of what goes to the screen. And there's certain conditions, such as like the borderless window, where it detects like, oh, I can save like a copy here, where like I could do the thing I do for rendering and just do like render a big rectangle that is just the window contents, but it's just a 1-to-1 pixel copy. And if I recognize like, oh, this is all that's going to be visible on screen at the time, Windows has a special case where like, instead of doing the copy, it just points the GPU at like, here's the data, here you go. Weird, very specific list, because it turns out like what GPUs let you render into versus what they can actually display physically is also like, there's usually some restrictions on what the display scan out hardware supports. So again, like there's this thing where like it's just the render targets have a list of pixel formats they support, and like scan out usually has like a much smaller list of pixel formats it supports. And then there's constraints like, oh, like you have things like the GPU can render in RGBA byte order or BGR byte order, and it doesn't care. But often you have things like, oh no, the display scan out hardware that actually sends pixels out in a 8-bit per pixel mode might only support BGRA and doesn't support RGBA byte order at all, because it doesn't need to. But there's all these kinds of rules now suddenly where like, oh, there's HDR modes, and like it needs to be in this specific thing, which is what actually gets sent to the monitor. But like if you're a game rendering HDR, you're probably using like a float 16 render target, or you might be using one of the one random target format where RGB and each have 10 bits and alpha has 2 bits, which is another pixel format, which might or might not be something that your GPU can actually output to the screen. So again, like there's all these kinds of random constraints about what this hardware can actually do that you're insulated from, because the OS will just figure it out. Like some of this stuff the GPU can actually directly show, and some of it can't. And when it can't, the OS goes there like, actually, let me help you out here and just insert like a very simple pass-through pixel shader that just copies the pixels from A to B and changes the format to something that display hardware actually understands. But again, like the OS has to do all this, and I was around for all this getting added layer by layer by layer, right? So like it was very, very visible, because like at the time you have the running example I was using was this mouse cursors thing. Initially, mouse cursor is just something that you have to render yourself. And then you have being advertised in PC magazines, which I was reading at the time. Like all these PC magazines, like they were like 30% ads at least, if you look at an archive. Like I saw one for like Byte magazine that was just like, Jesus Christ, it was basically 50% ads. Like every second page is a full page ad. It's crazy. But so you would have these PC magazines that you were reading at the time because they contained like program listings for you to type in. And like, there was a whole community around this of hobbyists. But they also have advertisements where they say like, oh, this is a graphics card that has Windows acceleration. And then what does Windows acceleration mean? And they tell you, because this was meant for enthusiasts, which says that, oh, this hardware has support for just copying screen rectangles, which is this whole thing that I just explained with the pixel format conversions. Like, yeah, if you're dragging a window around, this whole like copying pixels quick makes your experience a lot better. Like in Windows at the time, if you're drawing a window, it wouldn't actually move the window contents around and just showing you an outline, just like like 2-pixel outline of where the window would go. Because physically copying the pixels on these machines at the time was actually fairly slow. It would be a horrible experience. So it would just show you the outline. Once you released, it would actually move the window. And usually you could actually like physically over multiple frames see it like disappear in one place and like get repainted in the other place, because it took a while. And then you had graphics cards with like Windows acceleration. It's like, oh, this can actually move the pixels quickly. And then you could just turn it on like, oh, show the window contents while dragging, because suddenly it was relatively cheap. And you would still see like whatever areas you uncovered would need to be repainted, and you would see those repainted. But the window you were moving was actually current because it was using the acceleration. And they would tell you, this is a very user-visible feature. They would proudly advertise it. And they would proudly advertise that there's hardware mouse cursor support, which is the sprite thing that I explained. And of course, like initially this was just like, okay, like the usual like black and white mouse cursor. So it's just usually something like where it's just like a 2-bit per pixel mask or something. Usually like, oh, like this is like you're stenciling out a hole, which is like the black region, and then you put the white region on top, and these are 2 separate bit masks that you poke in the hardware somewhere. There's just a 16 by 16 sprite or something that the hardware supports that it will just put over the thing. And that was the hardware mouse cursor. And that made the mouse cursor like better. There was lots of these update glitches. It would move a lot more smoother and everything was nicer. So this was a very visible thing. And then Windows 2000 introduced like, oh, now you can send mouse cursors that have alpha blending, because you had a mouse cursor with drop shadow, which you don't see much of these days. I don't think that's not as popular anymore, but that was a big feature in the Windows 2000 days. And so suddenly, like they needed to go back to painting the mouse cursor and the software again on some GPUs, because some supported, like some didn't have support for this at all, the really old ones. Some had support for just the 2-bit per pixel ones. And like the newer ones were like, once we're like, oh, we're doing mouse cursors with alpha blending now. And the new GPUs then added like, okay, we can do alpha blending. That was not like that big a deal at the time anymore. But this is all stuff, you see these layers accumulating. And the stuff with embedded DisplayPort is just, I was again working on this Valve VR AR thing in 2012 and then 2013. Why do I know how stuff like DisplayPort and so on works, and how this whole latency stuff works? Well, I spent a couple months, straight up months, looking, along with several other people, looking into all this stuff. Like, how does your visual processing and your brain work, did a lot of experience with that, but also just how does the current stack look for just displaying the stuff on the screen. Some of this was stuff I had to learn. A lot of it was stuff I already had very present in my brain because I came onto this project of a thing I had just completed, which was working on a graphics driver. And guess what? You have a pretty good idea of what goes on in the whole like back end of your GPU, including things like display pipeline, if you've just spent a year and a half working on a graphics driver. It's very, very present in your brain. So like that part's like, that's all just path dependency. And now you realize like this is a peek behind the scenes for everybody. We had like a list of topics before the thing, and I resisted putting in anything more here because we started this question with like, oh, like how did you learn programming? And now I'm somehow into like explaining random hardware mouse code stuff for an hour.
It's great.
So like you don't, it doesn't take much to get me off on a random tangent. Anyway.
Now, then, after this introduction,
this is how this will go every time, by the way.
I know that you worked briefly for game company. You started,
yes,
right? And then you
yes
started working at RAD and pretty much worked on various projects. Now I know that you also did contracting for Valve while sort of being at RAD,
yep,
technically speaking. Can we take a couple of the projects that you worked on, either the early ones from games or from RAD, and talk a little bit about them?
For sure. I'll try to actually keep it brief this time. So like the first
we
thing...
don't need to be brief. We can be deep.
Sure, but just in terms of flow still, it's probably good if I don't spend that long on everything. The first thing I did had a bunch of demo scene stuff that's like hobbyist, that's not like work. I, as a student at university, I was the official term is studentische Hilfskraft at my institute. It's like student help or whatever, at the Institute of Computer Graphics at the University of Bonn. And they had a project they were doing in cooperation with some company in Munich, I think. Anyway, this thing was called 3D reality maps, and it was a geographical information system kind of thing where they had 3D scanned map data. Not actually 3D scanned, it was mostly like aerial images. But they had like these survey planes flying over them, and they had cameras mounted at multiple angles on the plane. So you had like very, very high-res photographs of like parts of the towns, and some of them were at an angle. And due to some of these images being at an angle, you had some idea of essentially parallax, and you could figure out the depth from that by aligning just all regular camera shots. There was no like LiDAR or range finding stuff, but you just had shots from multiple angles, and just by where features aligned in these different angles, you would still see roofs, but like one was straight down, one was like 30 degree or something angle this way, one was a 30 degree angle that way. And by how features moved relative to each other, you could tell how far from the ground they were.
But the goal was to say how far you are, or what was the goal? This was just basically aerial photographs, but you still want to get an idea of like the 3D structure. You basically want to like, if you think of like a classic terrain and stuff, what you want is a height map, right? Just for every point you have like height information. And you can sort of infer that from this information because you have different amounts of parallax if something pokes out. And this was like the images we had were from regions near the Alps. Some of it was towns, and in towns this doesn't really work. But for something like a mountain peak, it works surprisingly well. And so we had this gorgeous high-res map data. And that was just a product, like essentially like a commercialized terrain engine. Like the product was just like, hey, we have these nice 3D maps that you can fly around. And they had like support for things like shapefiles, is like the format that you use in these systems
to make all kinds of annotations. Like, for example, you have things like hiking trails, and then somebody goes there and just has like geographic markers where they like essentially put GPS coordinates everywhere. The way you would actually measure this historically, there's a million cartographic systems, and it's kind of a nightmare. But these days, just think of it in terms of like a GPS coordinates, where it's just like, okay, you put an angle. That's one way to put this. Like, so azimuth, elevation, whatever. A couple angles, longitude, latitude. And just put these timestamps, and then you can mark things like hiking trails or like roads, like all this, like just polygons and like vector graphics on top of like whatever terrain data you have. And dealing with some GIS stuff, which was interesting. You learn a lot about just real world complications if you deal with any real world data. Because like the GIS stuff is all like these data formats that they're using are from the 80s. It's DBase files, which is very telling, among other things. So it's like, that's when they started digitizing this. Like every kind of like commune, like city, township, whatever, they all have records because they need to like, what are the plots of land? Who owns what? And they need to have very precise coordinates. Like they have these going hundreds of years back. There's just a big book. Like literally, like in Germany, it's a Grundbuch. It's a literal book that's just like full log of who has ever owned like any plot of land. Like, and of course, they also need to survey of exactly what the boundaries of these are, because like that's the source of like the nastiest kind of neighborhood disputes. Is when people disagree on where the boundaries of their property lines are. That's, by the way, like if you ever want to like start beef with your neighbor, call an official surveyor and have them mark your exact property lines. It's great. Anyway, so they had all this data that's going back in Europe hundreds of years, right? Like into the Middle Ages in some cases.
Really?
Unbroken. Yeah.
Okay.
I mean, like you just have towns like Europe has like towns that are thousands of years old, and like they've not always kept records, but they've kept records for a long time. Okay. And it's not like oh, they surveyed, like they don't have GPS coordinates for something that was surveyed in the 1100s, obviously. But they do have things where like, oh, like they have like things with markers like, oh, like this property starts at this particular oak tree or whatever. And then once you get into the 19th century, you have cartographers like getting serious about this thing. Even in the 18th century, you have things like the French Revolution, and you have surveyors trying to figure out the shape of the earth. You look at like, oh, the circumference of the earth is like almost exactly 40,000 kilometers. What a coincidence. Haha. It's like, no, it's not a coincidence. Like it should be exactly 40,000 kilometers, because the way they specified this was originally like, okay, like basically take a quarter circle through Paris to the North Pole, and like that should be 10,000 kilometers. That was the purpose of the original definition. And if you look at it, it's like, first off, the Earth's not a perfect sphere; it's slightly ellipsoidal. So like the distance through the North Pole and like around the equator is not exactly the same. Also depends on exactly where you are on the axis. There's some error from that, but also like they had to survey this by 18th century technology, and they got within like, I think like a couple %, which is impressive, but of course means that today like, oh, the circumference of the earth is like some like 40,050 kilometers or something like that. Let me actually check out the real number.
I'm gonna count how many times I will ask you how the hell you know this, okay, in this podcast.
This is just something, so the circumference of the Earth is approximately 40,075 kilometers at the equator and about 40,008 kilometers from pole to pole.
Damn, that's close to 40.
So, again, like, right, so like that's something where you go like, holy shit, with 18, like they got it with like 4 decimal digits pole to pole. That's impressive. It's not quite perfect, but man, like, I mean, they had to do this with like navigating by the stars type shit. So it's like this is how they defined this. Anyway, how do I know this? This particular thing is because I worked in GIS. Because I just explained that you have these records going back hundreds of years. Guess what? Every single coordinate system that they have ever used is still in use. Because if you have like a record, like in a random township in Bavaria, right, that was surveyed at some point in the 1800s, and they set up their cataster, which is the record of like who owns which plots and like where these plots are, on that coordinate grid, chances are at least parts of that cataster are still on that coordinate grid today. Whenever they did a newer survey, in Germany, the main one is Gauss-Krüger coordinates, after C.F. Gauss, who also did a lot of this geodetic stuff. They would measure this stuff sometimes in the mid to late 1800s, they would remeasure all this stuff. But of course, you then don't go like, oh, let me rewrite all these books. What instead you do is you determine, okay, best fit between the new coordinate system and the old coordinate system. So like the entirety of Germany, and if you have stuff that covers the entirety of Germany, it's like the rail network. It's on a global like Gauss-Krüger coordinate system for the whole country. And then you have parts of like, oh, this township is surveyed on this older system originally. All the new records they're making are in the global Gauss-Krüger stuff. The old stuff is still whatever it was originally because that's the format all these records are in. And here's the official conversion from the one to the other. That's how all this works. But that also means that if you get stuff like a shapefile, it's in whatever reference coordinate system that was made for. And this is still ongoing today, right? We have GPS now. Newer stuff is probably recording GPS coordinates. The standard survey stuff up to like, they were changing their measurements of the shape of the Earth regularly. I think that's called the reference ellipsoid. That's just defining like, okay, what's the best fit? And of course, the Earth is not a sphere. Like it's also not an ellipsoid because it has mountains and things. It's not perfectly smooth, right? But turns out even Mount Everest, like compared to the like radius of the Earth, is kind of a rounding error. Like if you think of it, it's like, oh, this is another fun fact. Like yes, the Earth, because it has things like Mount Everest, is not perfectly round. But that's something like an 8-kilometer elevation on an object that, as said, has like 40,000 kilometers circumference, right? That's not a big imperfection. So in fact, Earth is, I believe, smoother than regulation billiards ball.
What? Really?
Like on the scale, yeah. Because if you think of it, like a billiards ball is like a couple centimeters across, right? It's like I don't know, inches, like 2 inches or so maybe. It's like something like that, less. It's something somewhere in that range. And if you go like, oh, like less than 1,000th error, that's like imperfections at the single micrometer level. Like you have machine parts that are machined to smaller tolerances than that. But like a polished billiards ball, like within a micrometer is just completely fine. It just doesn't matter at all. And it's just like, so this stuff is like, yes, like there's a lot of shape on the Earth, but like once you zoom out enough for something like, oh yeah, this thing has, yeah, I mean, you can work it out. Like it's 10,000ths of kilometers of radius. Yeah. And then like, yeah, plus or minus 10 kilometers, it's 0.1%. So the Earth is not perfectly smooth, but it's quite smooth, even with all the stuff that's on top of it. Anyway, so dealing with GIS, you learn about all this fun stuff with cartography and why you have this library called Proj for all the cartographic projections, because every country does its own thing. And why do you care? Like we had maps in the Alps. Turns out Germany is on one coordinate system, Switzerland is on another, Austria is on another. Then you have the fact, and this was a real fun thing to debug. We had cartographic data from the German part of the Alps and from the Swiss part of the Alps, and you looked at it in this app, and like for a while, there was this weird thing where there was like a straight up line right through the Alps where suddenly there was this big cliff, essentially, like, oh, everything dropped by exactly 35 meters, I think it was. It's like, what the hell happened here? What strange bug is this? The strange bug turned out to not to be a bug. The reason is, like, the altitudes in this survey are all of the altitudes you have in any survey are relative to sea level. Normal null in German, right? Like, so all heights are relative to sea level. Turns out, for the southern part of the Alps, the sea level you use is the sea level of the Mediterranean. And for the northern part of the Alps, the sea level everybody uses is the sea level of the North Atlantic. They're not the same sea level. The Mediterranean is, I believe, lower or higher, one of the two. And it's like, it's a couple meters. Like, it's like, so it's like you learn all this stuff like, oh man, the world is complicated, isn't it? So that was my first job, just dealing with that kind of thing. And like, I wasn't doing much of the cartography stuff. That was just stuff I was like sitting next to while it was happening. The stuff that I had was mostly like, okay, like people could like input hiking routes, and I just needed to like, in the app, I did some user interface stuff to like visualize that, let people print out their routes, whatever. So I had nothing to do with the cartography stuff, but because I was quote unquote on the development tree, I saw all the stuff going on as it was happening, which was fun. So that was my first job as a student worker there. Then I was at 49 Games, like a German game company, from 2008 until early 2010. That was a company founded by several friends, like demo sceners. So we knew each other already. Like, I was doing a lot of demo scene stuff, which we haven't gotten into. We might get to this at some point. So these were all people I knew already, and I was working with as part of like the demo group I was in called Fabrausch. And so we knew each other. They knew I was good. We had worked with each other for years at that point. So like, I didn't really have to do much of an interview there. They still interviewed me, as a matter of fact, but like, not to figure out whether they wanted to hire me, but just hey, like, we know this is somebody we want to hire, so we use this to calibrate our interview questions. Like, how difficult are these? How long does it take somebody who knows their stuff, whatever? Because if you're hiring people, like, you give people these interview questions and you don't actually know what, like, if you've given them like a couple dozen times, at some point you know what an average performer is, but you don't really know what the scale is, right? So it's like, okay, let me give you our usual program interview, just so we see like what a real good performer looks like. Basically, that was the idea. Do them? I don't know if I actually aced that, but like, it was just something they wanted to do. But so I was there for a while, and then because I was also fresh of this JS stuff, they needed a new terrain engine. I was like, well, I know a thing or two about this. So that's what I started doing there, and then also like editor stuff and so on. At the same time, due to my demo scene activities and other stuff, like, I had some interest in character animation. I had found Casey Muratori's website, where he had like, it was funkytroll.com at the time. Funky Troll. It was this old website.
I had no idea.
Funkytroll.com. Where he just had some write-ups like, this is like, we're talking early to mid 2000s era. He had some write-ups about his explorations into quaternion interpolation for animations and what the geometry of that was and so on. So I had found that because I found it very interesting. And through that found that he was running a forum, the Molly Rocket forums. He had like, his game company at the time was called Molly Rocket. There was mollyrocket.com, which had these forums. And so I started hanging around there because there was some cool stuff, and started interacting with other people on that forum, including one Sean Barrett and one Casey Muratori and one Jeff Roberts. So I was a regular on that for quite a while. And like in 2007 or early 2008, one of the two, I think it would have been early 2008. So before I had finished, like in 2008, I was still finishing up my degree at university. And Casey offered like me to put in a good word with Jeff. Like, hey, like, so if you ever want to work at RAD, because he knew me from the forum, and he thought I was potentially good. And it's like, hey, like, I can hook you up with Jeff if you want to work at RAD. I was like, cool, thanks a lot. I'm still just finishing up my degree. At the time, I was still living at my parents because I gotten into Bonn, which is a university close to where I lived anyway. It's like an hour commute. So it's like, okay, like that's not far enough for me to bother with like getting a dorm and whatever. Like this was just easier. So I was still staying at my parents. And it was like, okay, how about this? Let me not combine the whole culture shock of like, oh, I'm living by myself for the first time. I'm working like professionally for the first time with also, you know, moving to a different country and continent where I know absolutely nobody, all at the same time. Like, that's a bit much. How about like put a pin in this? I am in principle interested, but like right now, like let me first get into this whole thing, like get my shit together for a bit, and then talk to me later. I was like, okay, cool, we can do that. So, and that then ended up happening in 2010, where Jeff shot me truly a tiny mail. I didn't have a copy of it here. I have it in my email folder, but this is not the right machine. It was truly like a 1-paragraph, 2-sentence mail. Like something like, hey dude, want to work on like Larrabee for Intel and make mad cash or something like that. It was literally like that tone. And like looking at this, like, is this a joke? Who is this weird surfer dude? It turned out it was not a joke, and he was actually interested in hiring me. Sight unseen, by the way. Like the first time I met Jeff, he didn't even have an interview. Like he moved me over to the US, sight unseen. The first time we met was on my first day at work, which is wild. Come to think of it, like,
what?
The whole thing to get me a visa and so on all happened without ever having met in person.
He puts a lot of trust in Casey's, I don't know, like suggestions, recommendations for hire.
Yes, he absolutely does. Casey was essentially like RAD's #1 recruiter for a long time. Like, because Casey knows a lot of people. Jeff also knows a lot of people, to be fair. Like he also was just would also just randomly hire other people he already knew, but yes. So like this whole thing was wild. Anyway, this was just a thing where it was a fascinating project. And the other thing was like the company I was working at was paying me about average for a German game studio at the time. I had started out because it was still technically very junior. I had started out at junior pay scale, and like I did the whole terrain engine thing, and they basically upgraded me to like, okay, no, you're senior within like 3 months. Like, I could have asked for that to begin with, but like they also told me that during my interview, like, hey, like, do you want to see here and like more responsibilities and so on immediately? And I was like, that year, I don't know, like coming out of reaching that end of education, where like, okay, like all your life up to that point, you've been going to school and then like going to university, whatever, and you just knew what the next step was. And just suddenly like, okay, you have your degree, you're just out of stuff on your checklist to do. And it's a weird transition in your life. Like, I don't know about anybody else. I know it was hard for me, and it was very hard for my sister too. It's just a weird transition in your life where suddenly you need to figure your shit out and there's no plan for you to follow. And you realize like, oh, I'm an adult now. This is just my problem. I'm on my own. So I was just like, guys, I'm kind of overwhelmed right now. I have no idea if this stuff is going to work out. Like, let me put this on this whole junior thing and with lower responsibilities for a bit. Because like, I have no idea if I'm a good fit for this. I have no idea if this will work out. And then like, cool, we can do this. And then it once became clear, like, no, you're working out just great. Instantly bumped me to the more senior pay scale, which thanks. Like, didn't have to do that, but I appreciated it. But then the offer for RAD was going from like, okay, average like German games industry, which pays okay but not great, pay scale, to like, oh, West Coast tech programmer pay scale, which is a literally different order of magnitude. I think because this was also on a contract for Intel, And so if you're doing this whole contracting gig, these things are, contractors get more per hour than a non-contractor at the same rate because you don't have the same level of job security. Right? If you have like a fixed employment, at least theoretically, you have health insurance and whatever, and you know that, okay, you're probably going to have this job next month. Contractor can just get dropped at any time, and you just have to plan as a contractor for like, okay, any given year, I might only have 10 months of work. And like there's 2 or 3 months where I just didn't land a gig that I still need to survive and be able to pay rent, which is why contractors generally get more.
I was under the impression that in US, you're generally like, you can be fired from one day to another, and you know, like the job security 3 months notice period is like the EU standard thing.
The 3 months notice doesn't. There's usually a 2 weeks notice, and like with cause you can get fired instantly still. There's still usually a thing where they could, in principle, they probably normally won't unless something happened. So their thing there is, you absolutely have in things like, especially service industry jobs, like if you're any kind of food service thing, stuff like that, where it's easy to get, relatively easy to get replacements, although also not so much anymore, because it turns out, like, especially around COVID, that was suddenly a less desirable job. But for stuff like tech industry, the issue is it takes a long time investment to get somebody up to speed. You can't just parachute somebody into a new code base and have them be productive within a week. Yeah. Right? It takes a while for you to like just need to get them set up. They need to get their machine set up. Like there's always some kerfuffle where like your credentials don't really work for everything you're supposed to have access to, and just
for something, yeah.
It just takes a long time. Like it's like a couple weeks to shake that kind of thing out. So in general, like yes, in theory, you could fire somebody immediately. In practice, you have some investment in getting them to be productive at all, and you don't want to fire them immediately. The contractors thing, like, so for example, if you have something like Unreal Engine, you will have contractors who are familiar with Unreal, and they can contract for AFAIK. They can also contract for other studios that do Unreal projects. There's still some startup period to adapt to whatever their project is doing, but they have a lot of skills that transfer. It's not like you just get some random IT contractor has never done this before. So like they have a slower start, they have a much faster startup period, and they're sort of more interchangeable in a way, but they're still like a lot of the same people. But like hiring somebody, you have some investment in just getting them to be productive at all, and you also therefore aren't that quick to fire them unless something really bad happened, or like your business is not doing well. Then they're the first on the ejection seat. But that's also a different thing. Like in general, like people will not, they would rather take somebody for a while longer if they're not really working out well, but they are still getting something done, over somebody that, okay, this might be great eventually, but like there's another month of like, okay, this person is basically a write-off because we need to get them up to speed. There's just a weird situation there. But yeah, employment laws, it's also very dependent on the state, right? There's like, for example, in California, non-compete clauses are illegal. Other states will allow this kind of stuff. It's like they just put in your employment contract that after you've quit a job, you're not allowed to work at anything related for X number of months, 6 months or something. And like in California, you just can't do that. I mean, you can't write it into the contract. It's not enforceable. The courts will just say like, no, this is not permissible under California law. But elsewhere, they do put these clauses in and they are enforceable. And often people still do it anyway and then get sued and whatever. There's settlement, blah, 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 blah.
So you're joining...
In Europe, this kind of stuff's not allowed.
So you're joining RAD. Back to the topic.
Yes.
Joining RAD.
Yes.
Awesome salary. Contractor salary, so even higher. And...
Yep.
What do you work on?
Larrabee. the software stack for Intel's ill-fated GPU effort. So this was already like after, like there was the big announcement in 2008 or so, I think, also for this. That, oh, we're doing this, blah, 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 blah. By 2010, that project had already gotten suspiciously quiet, and it was kind of clear that it was a bit of trouble. And there was a lot of random fun bullshit about it that I won't get into here. Like this is like the kind of stuff, like I can talk about this at length in person. It's just like, I don't know, like so much has been said about this project, and like all the outside views of seeing this are hilariously wrong in what they think were the actual problems. There were some technical problems with the whole thing, for sure, many of them, but like the biggest problems that I saw were just all organizational, where this was a deeply dysfunctional project top to bottom.
Okay.
And especially like so RAD was working on this because Intel had this plan to do a like lots of cores like add-on board, and like with the idea of graphics being a killer app for this kind of thing. Sort of, not really. Like I think Tom Forsyth will often spin it a bit more like this than it really was in my mind. But anyway, like sort of the way like GPUs with CUDA and so on are going now, where like they're mostly AI accelerators that happen to also be able to do graphics originally, but that's not really what the main thing is. It's this kind of thing like, oh, this is a massive vector machine that had a bunch of additions that was supposed to be also good for graphics, but it was primarily meant to be like, oh, this is just a programmable computing device that you can do to do very programmable graphics with, but can also do other stuff. That was the vision. And the thing was that was always clear was like, oh, this also still does need to be a competent GPU. And if we do this, we need something that can turn this into a GPU. So we need a software stack that just makes it look like a regular GPU. And RAD had a product at the time, Pixelmatic, that was a software renderer for D3D9 level hardware that could like do D3D9 era fixed function or later vertex and pixel shader stuff, and just software emulate that. Not even emulate, it was just run the shaders in software, right? So they bought Pixelmatic from RAD along with the team to work on what was supposed to become their graphics stack. And then there was a lot of back and forth about this, and like different teams that had a different fork of this. And then at some point, Intel decided like, okay, we really want to ship this. And suddenly this team went from 50 people to 500 within a month, which was just chaos, of course, because now suddenly nobody knew what they were doing. And then we just basically like had to, like, there was a thing where we then like essentially revoked Perforce access on our Perforce, the version control for the Intel people, because suddenly there was, no, because the problem was, you suddenly have like 500 people like checking in random commits, and suddenly at no point is the version control ever in a state where anything even builds, right? Because everybody is like, or at least not the whole thing, because like we have 500 people, so they have like whatever, a couple dozen check-ins a day suddenly, and everything is always breaking something, and they will always fix it within a couple hours. But like by that time, something else is broken, and so suddenly like we're just like lost all ability to get anything running. And I say we, I wasn't involved at the time. At the time I joined, this fork had already happened. It's like, okay, like we have a separate Perforce, we take regular merges, but that needs to be something like you need to have a stabilization period where you like fork off a branch, get that to compile cleanly, then we take your merges. Otherwise, we're not getting anything done on our end of the thing. So I joined, and there were a bunch, like the part we owned at RAD was the part that essentially emulated a fixed function. The stuff on a GPU that's fixed function. You have the Larrabee CPU cores, which were the equivalent of shader cores, and they're just things that run code. And to make it act like a GPU, there's the actual graphics driver layer, which implements something like D3D10. And what that ultimately does on every GPU is you take the draw commands you do and write them into some byte format into a command buffer, which is just a byte stream, like draw this many primitives, set index buffer to this thing, blah, blah, blah. It's just a record of the things you do that gets submitted to the GPU, which then reads this and performs the operations. Like that's how it works in every GPU. And that's how it worked on ours. So there was the graphics driver stack that did that. And then we got this command stream, had to then parse it and then render stuff, ultimately. This whole question, the issue with that product on a high level was if you have a actual GPU that has things like, okay, there's, for example, a fixed function rasterizer, which is just this block of hardware, some unit of something that was designed, where like every couple cycles or whatever, you can pipe in a new triangle, just a description of like where that triangle is on the screen. And it ultimately outputs a list of like, here's pixels covered by this triangle, and here's where they are on the screen. And then enough information to figure out, like if you have texture coordinates and so on, to figure out what texture coordinates should be at that pixel. There's just some amount of data that needs to come out of that. But the rasterizer fundamentally is primarily a thing where you put in the coordinates of a triangle and you get out essentially a stream of like, here's a list of pixels that now need to get shaded. And in a regular GPU, that's just a hardware block you design has certain capabilities. Like, okay, we can take this many triangles per second. Like, for example, like we can take a new triangle every cycle or every 4 cycles or something like that. And then we also can output this many pixels. And of course, we can't accept a new triangle when we're still working on the old triangle, and that maybe there's a hierarchy, blah, 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 blah. But it has certain specs. And these have changed over time, but you still need to design the thing and it needs to have certain specs. The issue was in a hardware design, you just have to commit at some point. And it's like, okay, we're going to build something. It does this, and that's what it does. And that's what we're going to build for this generation. And if that sucks, oh well, better luck next time. In software, because any change, even a potential like big architectural change, is right only a software update away, right? It's never something where it's like, oh, we can't possibly do that. I mean, we need to write the code, obviously, but it's never something where it's like, oh, the hardware actually can't do that this generation. It's always something like, not sure if we have the time, but it's something we could do. So there was just like my view of the biggest problem with that project was that everything was just a fractal of like, oh, we could do this. And if we do that, then we could do this and blah, blah, blah. So we just had like all these ideas of like everything could be like a microcosm for the whole project for me. Is there's this function, the 2D blitz that I explained earlier for stuff like mouse cursors, but like, oh, copy pixels from A to B. That was also something the GPU needed to do, and that's also due to the way the rasterizer worked. It was a tile-based rasterizer, which means we had like regions of pixels, and like sometimes you need to like copy them from like the render target format to an internal working format and back, because it's like the internal working format was slightly different when we're working in these big pixel tiles. So we had these routines that would either load something from the render target format into the working format or store the working format back into the render target, which was basically a slightly fancy memory copy kind of thing. But it was all software. And there was this long list of to-do, like, what if we prefetch this way instead of that way? What if we do this? What if some of these copy backwards? And so we had a file, C++ file, just with these blit functions for like different combinations of different pixel formats. That was all C++ templated up, was still 450 kilobyte of C++ source, one file. That took, I believe it was 2.5 minutes to compile every time you edited it. That one file.
Okay.
One file. With the Intel C compiler that we were using, which was not very fast, but it was just torture, right? And I was looking over some of these because we had some weird behaviors with some of this. This was like later, actually. This was not the first thing I did. This was like well further on, but like we had some weird behavior with that, and it turns out like, yeah, there were like hand-tuned prefetch amounts and some of these just like, oh, somebody had typoed these numbers. Instead of like 21, it said 12. And suddenly like the perf was bad. And like you look at the stuff like, okay, it's not like you can't have this kind of bug in a hardware implementation of the same thing as well. But the issue was like everything was always up in the air, right? It's like, okay, like this splitter thing is not just a hardware block that does what it does. It's like, no, it's something you can touch and edit at any time. And then somebody realizes, this part of the pipeline would be slightly better if instead of RGBA, we stored them in BGRA channel order. And then like, then we need to change the shader compiler too. And like suddenly like everything is interconnected with everything else and everybody is trying out these things. And like, there's just, because it's, at the same time, things were too easy to change and too hard to change. Too easy to change in the sense like it's software, right? Everything is up for debate. Like you can just change this. And too hard to change in the sense like, yes, you can all change this, but every change you do means that you also need to do changes to thousands of lines of code elsewhere, not all of which you were immediately aware existed. So people kept changing these things and kept like trying wild shit. And we were just trying to like still figure out some architecture stuff about the way this should work at the high level, all while these details were constantly changing under us. So it was just that was the biggest problem. Like no GPU, like if I had to point at a single thing that failed about that project, it would just be the idea like, oh, we're just gonna start essentially a brand new GPU from scratch and do it in software. But the biggest part is honestly just to start a brand new GPU from scratch. That's just a hard thing to do. If you look at basically any GPU I can think of that exists, like didn't start out from just somebody having absolutely nothing and going to like, oh, we're going to do a D312 level GPU immediately, clean slate design, not having ever done this before because this team had not done this before. Intel had their own graphics team that had their different GPU that had been iterating on this for a while, but the team that did this, including the people at RAD, had never actually built a GPU. And turns out there's a lot of degrees of freedom in that design space. And the same way, like every GPU you look at, just like through acquisitions or something, goes back to a team that has built a slightly smaller, slightly simpler GPU in the past. And they are from a team that has built a slightly smaller and slightly simpler GPU in the past. And then you trace that path back. And it goes to one of a handful of places. Like almost everybody who has ever built a GPU has some lineage to people like Silicon Graphics who did this in the 80s. Mm. And like they or like there's like Silicon Graphics people, there's like people from like 3DO or like there was 3D Labs who also did their own completely independent thing in the early GPU days. There's of course 3DFX with the Voodoo people. There's a handful of companies, but even they usually had some connection to like Silicon Graphics or similar. So like you have a long lineage of people who have worked on something like this before, and everything they do is slightly more sophisticated than the thing they built before. So if you look, for example, how the original 3DFX Voodoo worked, that is essentially a hardware that's just hardware that basically pretends it's a draw a texture map triangle function, essentially. That's how that works. It's still a command buffer thing, but you have to do a bunch of calculations to the GPU where like, oh, like you have to compute like certain vectors about the triangle edges. Like you don't pass the coordinates in like texture coordinates and it figures out the stuff yourself. You have to figure out like, oh, there's this thing that loops over pixels and needs to add this increment every pixel. And like in the driver, quote unquote, in Glide, the 3D API for 3DFX, there was just a function that did all this computation and just put in like, oh, this thing that needs to get added every pixel is just something that is computed in software and is passed into the driver. So like this thing was essentially like the original Voodoo hardware was basically like, okay, this thing is a draw a texture map triangle function that has like a couple optional features that can also like do Gauss shading, but it's a very, very simple thing. And the same with like GPUs. Like the original GPUs started from like these Windows GPUs. So it's like, oh, it's a thing that has originally just display hardware, and then we added a bit to be able to copy rectangles and maybe draw lines. And then we added a bit like, oh, draw texture map triangles. And then we added a bit like, oh, set up those triangles so you can just like set the transforms, and it can do the, like that happened in the early GeForce days. Like the GeForce was the first GPU with hardware transform and lighting, which meant that instead of this thing where you just send it like fully chewed triangles, and it's like, okay, we just need to texture map these. Like this thing, you could give it like 3D vertices and like this matrix, and like as long as it was one of the things the GeForce GPU supported, it could do like transform calculations and clipping and so on all there. Like originally GPUs couldn't do that. The big silicon graphics workstations could do that. So that was a model that they could follow, and that's where things like OpenGL. OpenGL comes originally from IrisGL, which is the Iris graphics library for silicon graphics Iris workstations. So it's like this whole model, like we knew OpenGL was a good match for what you could reasonably build in hardware, because it was originally an abstraction for a particular piece of graphics hardware designed by Silicon Graphics, right?
Wow.
So all this stuff has a long lineage. And of course, by now, OpenGL, like with everything that happened in the meantime, it's just a complete mess, because like you have 4 decades worth of random features that got added, and there's just no shape to it really. It's just whatever, which is why they had to clean it up around the GL3 and GL4 era. And that was still not very successful. But the whole thing is like there's always this long history. If you go for CPUs, it's the same way. Like there's a few teams that design like completely new CPUs, and they're usually not very successful. It's not that they can't get it to work at all. It's just that there's a lot of just nuts and bolts knowledge of like, oh, we've done this before. We know what to not do, and like basically any successful CPU team that you can name today traces back again to like a handful of companies, and this is just people that have done this for the past 30 years. There's not many people, for example, who have ever successfully built a new out-of-order CPU, and they keep just they're nomads, and they keep changing between these companies, because once you've been on one of these products once or twice, you understand a bit about how this works, and you have an idea of how to put this together. But it's not something that, as a complete outsider who has never built this stuff before, you can really do. There's textbook knowledge of like high level, like you have a 30,000 foot view of this, of like basically what needs to happen, no question. But there's just a lot of just random gnarly details, like, oh, what do we actually do if there's this asynchronous interrupt that happens during blah, 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 and like how do we structure this so it just doesn't kill us? This is stuff you don't really think about. And it just helps to have somebody who's like, no, we've done this a couple times and we did this. It has these problems, but it works okay.
What is the proto company for CPU? Like Silicon Graphics for GPU? What would be the equivalent?
There's no single company that's done this, but there's not that many that have ever built out-of-order designs. Like teams that have built this. Like this was invented, I think IBM ACS, I think was the name, ASC, some advanced computing system, something. Like the idea is very old, 60s. There's Tomasulo algorithm, which is one of the standard out-of-order techniques, basic out-of-order techniques. That was the floating point unit for the IBM System 360 Model 90 FPU, I think.
How the hell you know this? This is...
So that's where that originally comes from. And you had other people like Lynn Conway, who did also some out-of-order-esque thing for, I think, the IBM ACS, which was a design that never actually got built. Lynn Conway is relevant here because she she is trans, which in the 60s was a bad time. And once that came out that she was trans, she got fired from IBM because of it, and then got a job in academia instead. And she ended up there's also Xerox PARC and whatever involved working with Carver Mead at Caltech, I think, and wrote a very, very influential book called Introduction to VLSI Systems. That this whole thing where you have like this notion of die shrinks for like process shrinks, like, oh, like the whole blah nanometer thing, that basically goes back to them, because initially, like, oh, we had like this thing, like we had integrated circuits, and like every process was very, very custom. And what they did, like they had this idea, like we're pretty sure we can design these photo masks in a way, like every process has these limitations. So it's like, oh, features can't be more than this close together because otherwise they bleed into each other. And like, you need to have like corners need to be 90 degrees and like this spacing needs to be like this. And if you put a metal via and whatever, it needs to be at least this wide, blah, 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 blah. Long list of rules. And they had this vision like, okay, they had worked on designing actual circuits before, both of them. And they had this vision like we can look at these integrated circuit processes and do a set of design rules, like these kinds of rules, that are much looser than the like official like production scale rules would be for like any particular process. But that means we have enough tolerances that you can basically manufacture this on any fab. And also, if we have a better tech in the future for like how we do this, we can just scale down the whole thing and it's fabricatable at a smaller size. So that was the idea of these design rules, that you can just scale down. And that was a radical idea at the time. They did a whole university course. This is a fun thing. They taught a university course on this. Like, hey, just to unsuspecting, like graduate level, but still students, like, hey, this is how you do VLSI design. Like VLSI was the keyword at the time, very large scale integration of like large scale integrated circuits. Because at the time, like the stuff you would be producing, like a lot of even like big computers would be built out of like discrete logic elements, like whatever, 6x NAND gates or like 6 hex inverters or stuff like that. Literally just discrete logic chips, like 12 pins, and you wired it up. And they're like, no, like integration is the future. And this way we can teach people a practical skill that we are confident will work. And they had connections to, I think, somebody at HP, which was still like a big, today you think of them as a printer company. They were a big, just tech company. And they had their own fabs because they were doing calculators and stuff. And they had connections to somebody at HP. We're like, no, as part of that course, if you're enrolled in that course, like as basically the term project for that course, they had the connections to get a wafer fabricated. So students could do their own hardware design as their term project, and it would actually get fabricated. They invented what's now called a shuttle wafer, where the idea is like, normally, when you're testing electrical circuits, like you have like all these copies on the same thing, and instead they did a mask where like, oh, we did one mask with the products from all the students. So just like 20 different designs, right? Every student had their own design. And that's merged them all into one mask, and that's what they had fabbed. And did that on what we now call a shuttle run, which is the thing, a multi-project wafer where you take multiple different integrated circuits, put them all into the same mask, run them through the fabrication once, because that's the expensive step, making the mask and like fabricating it. And then just make a couple hundred of them and dice them up differently. Literally saw the circuit in different pieces, right? Just have enough spacing between them that you can saw it into pieces. Like you made 100 of the whole wafer, and like each of them, you have 10 designs, and each of them gets like 5 copies, and hopefully one of them works. And that way you can do a much cheaper run for everybody involved, because you need to merge the cost of like doing the mask and so on across like all 20 people. Now with current processes, you couldn't do that because masks are ridiculously expensive. One set of masks for like current generation IC is like $10 million. But this was the 80s, and they could still do this. It was not like they had the connections to make this happen. Basically used like the off time that the fab wasn't used, which is also not a thing anymore. And that had people like, I think James Clark of SGI had like the prototype for his geometry engine was on one of these VLSI design courses. I mentioned all this. So Lynn Conway was one of the people who like was one of the co-inventors of out of order scheduling with her work there. But due to this whole thing with Conway and like Carver-Mead, then also turned into this thing that spawned a bunch of Silicon Valley companies, including Silicon Graphics. So this also all spawned, it's all the same people. Like every time you dig, it goes down to so few companies. Now microprocessors were invented by Intel. Like originally this was for a calculator. Like they just like did a chipset for a calculator, and like the first microprocessor was the Intel 4004, which was like a couple thousand transistors, and it was meant to be for a calculator. But then that turned into a business. And then like bunch of RISC CPUs, that goes down to like this is interesting for like the reason I mentioned the Carver, Mead, and Conway thing is like that's now the start of the 80s, and suddenly for a brief window of time, like through this thing, because they got these industry contracts and the Mad Lads actually made it work. Like for a while, like for a brief window of time, couple years, they were able to give graduate students the opportunity to actually like design hardware and have that designs fabricated. And a bunch of people come out of that, but also stuff like the whole Berkeley RISC project comes out of that, because it's now viable for students to like design a simple CPU. And MIPS comes out of that. So like two of the whole RISC wars in the 80s start out of this, of just suddenly students, like university level students, being able to do hardware on essentially like not the leading edge, but a reasonably new process, and like work on basically the same tech that was previously not accessible to anybody. So a couple of teams start there, but they start with very, very, very simple in order CPU designs that are designed to like part of the RISC thing. It's like there's a whole ideology around like, no, these things need to be very, very simple. And it's like for the environment they were in, there was a necessity, because they didn't have the resources and testing. Like they couldn't do like a complicated design and be able to test it properly, because this was done by a couple of grad students as their homework project, right? It had to be as simple as they could possibly make it. And then the RISC thing turns into a whole ideology thing once it becomes clear, like, oh, no, these designs are actually really cool and we can clock them really high because they're so simple. And like that goes sort of off the rails a bit later, where now it's a dogma thing, and like that's also wrong. But like the basic idea was just like these RISC chips were as simple as they were because they had to be, because it was a design by grad students within like half a year. And like anything that's not simple is just not going to finish. It's not going to work, right? But yeah, so that's where you get this Cambrian explosion of like different CPU architectures in the 80s, because it's not just graduate students who figure out like, oh, it's suddenly relatively easy for a small company to make chips. You have, this is a bit earlier, but not much, MOS Technologies, the people who did the 6502 and the C64 and others. That's the company, like this ex-Motorola people. Motorola was one of the big CPU vendors at the time. And they had an 8-bit CPU called the 6800 that I think was $100 a pop. And MOS was like, no, we can do a much simpler 8-bit CPU. And we plan to sell it for like a couple dollars, single digit amount, right? Because the idea is like, yes, we make a lot less on each individual unit, but this is capable enough, especially for microcontrollers and so on, that this unlocks a whole new tier of people using computing and things they otherwise wouldn't, because these things are so cheap, which was exactly right. So MOS Technologies happens in the late 70s as part of like, suddenly there's this window where reasonably good fabrication of integrated circuits is reasonably cheap. That happens during this time. Around the same time, you get DRAM. Like before then, memory was just magnetic core memory. It was just like weird, like it was horrible. Like you have this grid of wires and like magnetic rings around each of them. You have to basically weave these things together. Like I saw one in a museum one day. It's like you have 1024 bits of memory, and it's literally like 32 wires this direction, 32 wires this direction. Each ring is an intersection, and it's like, it's this big. So like, right? So it's like, this is 128 bytes of memory. You look at this, and it's
you can
this
look at
big.
each one of them.
Yes. So it's like, okay, like that's not a memory technology that works. And suddenly DRAM, like initially, like DRAM was horrible. It barely worked. Like literally, like I think 30% or so of the chips actually worked that you bought. Like the rest was just DOA. Because this was before they had figured out how to like, this was also, like this was from Intel. Intel was originally a DRAM company. But Intel at the time was a classic Silicon Valley startup just in a shed somewhere, essentially. Not quite a shed, but just a random warehouse. They weren't doing this in a proper grade 1 clean room. They were just like a bunch of people like a weird move fast break things startup doing stuff like by the seat of their pants. And like their DRAM thing was a great idea, but it barely worked. They eventually got their shit together. All this stuff is happening. And you have this like bunch of new CPU architectures, bunch of new things being done in hardware. You get the home computer revolution of the 80s, which was at the intersection of like suddenly there are cheap CPUs, namely the 6502 and the Z80, and B, suddenly there's cheap DRAM. And you can actually make a machine that has not just like 128 bytes of memory in SRAM, like the Atari VCS. No, you have like machines with kilobytes of memory. If you have 128 bytes of RAM total, that works if you put your program on a ROM cartridge for like a very, very simple video game system, but that's not programmable. Like you don't have memory to store a program. If you have a machine with 64K of RAM, you can put like 8 kilobytes of basic interpreter into ROM, and then like have like actual like 40 kilobytes or something for people to write their program into, which is like reasonable. And then that's how you get things like the C64. So all this stuff happens, and it's all like due to this intersection of like suddenly silicon manufacturing is cheap. You have these people, like the CPU designs come out of the whole VLSI revolution kicked off by Conway and Mead, which are ex-IBM people, or at least Conway is. It's just weird. All of this is intertwined. And then all the newer CPU designs you get are usually inspired by some things that came out of this. All the risks are inspired by like the Berkeley risk turned into Spark CPUs, still sort of around. The Stanford effort turned into MIPS. Originally microprocessor without interlocking pipeline stages. That's what MIPS stands for, not million instructions per second.
Say again.
Microprocessor without interlocking pipeline stages. And there's also like million instructions per second, which is also another form that MIPS is used. But the MIPS in MIPS technologies originally stands for microprocessor without interlocked pipeline stages, meaning there's no stalls. Except that was true for their initial prototype design. The very first one they actually shipped had interlocks. Because so the thing originally like didn't have like, you issued a load from memory that wrote to a register, and like you could access that register cycle after you did that, but it wasn't ready and would just give you garbage. Initially it was like, yeah, whatever, if you don't need the result immediately, just put a knob in there. And then they tried that. It's like, oh, cool. The programs we're compiling are 10% knobs now, and it's actually a problem for code size. It's like, okay, screw it. Put in interlocks. Like if you use them immediately, we stall for a cycle, whatever. So like that part of the ideology fell off immediately in the face of practical evidence, and those kinds of things would happen a lot with similar things like branch delay slots and so on. There's a whole, like, I'm not gonna get into that bit, but like, there's a whole evolution here, and like all these simple CPU architectures, like ARM, the ARM CPU, another like Sophie Wilson, another trans woman, who visits Western Design Center, who's the company that the MOS Technologies thing that did the 6502 turned into, because they were in the UK, and they originally were designing microcomputers for the BBC. They had the BBC Micro, which was another 6502 based home computer. The Amstrad CPC I mentioned was another one of these British ones. And so they were visiting this company because like, man, we'd sure like to build our own computer. But like they're like thinking like, oh God, this is some space age technology stuff to fabricate chips. And they visit Western Design Center because they're buying 6502s from them at some point in the 80s. And they realize that this is just some small company in a random office park. And they're cutting these masks by hand, but they're looking at this like, well, this is a lot less high tech than we thought. I think we could do this. And so they designed their CPU design and write an emulator in their own BASIC dialect. Sophia Wilson wrote BBC BASIC, which was the BASIC version they had. Not one of the Microsoft ones. They had their completely own BASIC, which was awesome. Wrote a simulator for the original ARM in BBC BASIC, then ported the BBC BASIC interpreter to ARM as sort of the first ARM program to run. I believe they actually ran BBC BASIC ARM version inside the ARM simulator written in BBC BASIC on a BBC Micro or something like this. It was crazy. Like they do this to debug the design, making sure that the architecture works, and then do their own thing. That's how ARM happened. The Acorn RISC machine was originally for the BBC, for the Acorn Archimedes, which was their successor to the BBC Micro. That's where we got ARMs from. But this all goes back to like this weird stuff like in the late 70s, early 80s, with a combination of like this infrastructure from being able to like do like semiconductor runs on the cheap due to the shuttle thing from the VLSI revolution thing, and cheap DRAM. This is where this all descends from. We suddenly get all these CPU architectures, and then basically like, we haven't gotten much in the way of completely new architecture since. Like there's many more actually that I didn't mention, but all of them are like these weird fly-by-night operations. And the fun one is ARC. So this is like the Super Nintendo Super FX chip. Like there's Star Fox 64 on the Super Nintendo. Super Nintendo is like the chip in there is like basically a extended version of the 6502, which is like not enough to like do fancy 3D graphics. It just doesn't have the horsepower. So they want to do like a 3D flight sim kind of game, which is Star Fox, on the Super Nintendo. And that system was set up so that basically the data bus just goes out onto the cartridge. And it's like there's ROM in there, but you could also just put extra hardware onto the cartridges. Like they had stuff like, oh, we can put an extra sound chip in there if you want weird sound effects for your game. It's just the same way, like the thing you put in a SNES cartridge slot is basically like a PCI slot, right? It's just a device you plug into the thing. So it can be ROM, but it can also have other things. And one of the other things they put into for Star Fox is this Super FX chip, which turns out is just a whole separate CPU. Designed by Argonaut Games, did their own RISC CPU to run the polyfilter and whatever stuff on that just does the 3D rendering. And that turns into like ARC is the Argonaut RISC core, which was then like some random CPU architecture that until like the early 2010s, that was the thing that ran like the Intel management engine on Intel CPUs, because this whole thing turned into just a microcontroller type thing that you could just license and put into your designs. It's like all of this stuff is interwoven in the weirdest possible ways.
How do you,
to
but
finally
how do you know this? Like, how do you trace it
because I
back?
care. It's because it's super interesting.
But from where? Where do you read about this?
This is history that you can just find. Like you can just look at the history of ARM, look at the history of like Intel management engine, SuperFX, any piece of hardware. It's so easy to find if you just Google things, and like there's all these history sites. It's very, very cool. And like especially the thing is like, of course, like if you look at any one of them, right? It's just like, oh, like this is a random thing that happens. But like if you have an interest in this kind of history, and I definitely do, like you read like 4 or 5 of these, and suddenly like you see all these connections, and it's like, holy shit. This is all like the same names keep cropping up. Like, oh, this person went there and then they did this. And this person went there and then they did this. Yeah. It's so weird.
This map.
It's so cool.
Map and like, you know, with the names and then the threads and then you like stick under the board.
It's full conspiracy theory. But anyway, like you have this thing with GPUs where like, oh, like it's not like this, like, there's never any independent invention. There surely is. But like there's a couple companies, like in graphics, it is like Silicon Graphics is one of the big ones. Evans and Sutherland is another big one. There's so much just traces back to just a handful of teams. And this person worked with this, and then they went to work with them. And this team worked with this, and then they went to them. So for another example that's very, very fun, the chip that's in the Nintendo, I wrote games for the Nintendo Wii at my job at 49 Games. So this was 2008. So I deal with this hardware, and it has its CPU is a variant of the PowerPC 750 CXE, which is a variant of the PowerPC G3. Essentially, that was in the G3 Power Max.
I can't even repeat that. And I can't even repeat all of the letters you say. But
PowerPC 750 uppercase C, uppercase X, lowercase e. That's a chip. I'm pretty sure. That's the variant. Like the actual chip in there is called Broadway, I think. But that's a variant of. Like they later sold a variant of that design, which is descended from the chip that was in the original GameCube, where it was called Gecko. And so this Gecko design is based on the PowerPC G3. And you look like who designed this. It's like, oh, it's like a team around a guy called, I think it was Brad Burgess. And you look at what did the guy do afterwards. It's like, oh, he's one of the chief architects of the AMD Jaguar, which is the chip that went into the PS4 and the Xbox One. It's like, huh, these are all the same people, huh? And then you go like, oh, like the guy like who was the chief architect on Zen, where did they come from? Oh, they were originally like at Digital, like designing DEC Alpha chips in the 2000s. And then they were at AMD earlier, and I think on the K7 era. Then they went somewhere else, and then they went back to AMD and did the Zen. And now they're doing, like, Jim Keller is now doing stuff with RISC-V. So, like, okay, so that team is a thing. Then you look at, like, it's all this, like, you see, like, these people migrating constantly, and it's just, like, the same names cropping up over and over again. Because it turns out there's not that many people that have ever designed one of these things. And, like, either they want a new challenge, or like they get fed up with the company, they get screwed up in some way, or just they want to do something else for a while, but then they come back to it. It's just, these names crop up all over again. So for another example would be the person, like the AMD Athlon K7, which I had an interest in because it was one of the CPUs I had. So I like was interested in how that CPU worked. There's a very cool site called chip-architect.com that had annotated die shots of the Athlon K8 and goes through a bunch of patents now expired, which is why I can mention it. It's like this, all the US patents they filed on how this design works. And just a die shot, like here's the physical layout of the die. That's amazing because you can literally see like, oh, like it's a 64-bit CPU and here's the data bus, and the data bus is even like split up for timing reasons. There's like other buffers every 8 bits. So it's like literally like you can number through bits 0 through 63, and like every 8 bits, so every byte, there's even a bit of spacing in there due to the way they lay out the thing. So you can look at this entire thing like, oh, physically there's a data bus that goes through here, and you can see everything that plugs into it. And you can just annotate it. Here's the LU1, 2, 3. Here's the scheduler. Here's like the FPU. It goes here. Here's the data load store unit. Here's how the renaming works. It's like all annotated with the patents. You look at this stuff. And it's like, okay, like there's some weird stuff with the division unit. There's no real hardware divider here. There's a separate patent there. I'm curious in hardware arithmetic, so I looked this stuff up. There's papers on how the divider in the K7 works. And it's by somebody called Stuart F. Obermann. So you do on Google Scholar, do a search for Stuart F. Obermann. And you find a bunch of things, including that's the same guy who then went to NVIDIA and designed the unit that does, there's like the interpolation for like textual coordinates, where like, oh, like I mentioned, like you get like pixels back, like you're doing the pixel rasterizer, you have the position on the screen, and then you need to turn that into like actual interpolated textual coordinates at that position. He designed the unit that does that because there's a reciprocal and whatever involved. Like he has the design for that, and it's like, oh, multifunction interpolator with built-in square or something like that is the thing. And like that goes into like how the sine and cosine on these GPUs works, and as far as I can tell, they still use that thing. Then you have somebody else, like I forget the name, another thing with S. Anyway, like that guy did weird ass design for the Intel Itanium, which was ill-fated. Like has just crazy talk about how the logic design for that worked, because they wanted to make the load store unit super low latency. You look up where that guy ended up. Oh, that guy is now at AMD and does like packaging design for Zen, and like that's the same guy who's like behind like AMD GPUs. Like they now have like the new big GPUs for AMD have this chiplet design where the memory controller and there's a big GPU die in the middle. Like the same guy who worked out that is like did Itanium stuff way back when and so on. It's like everybody in that industry who has worked there for a while has a crazy list of projects they've worked on. It's just like that. There's not that many people who actually do this. And like if you want to actually ship anything, you just have to hire people who have already done this before. There's a couple competitors, right? So
it's interesting that it's very difficult to start it from scratch, not because of the like technical reasons, but more about this tribal knowledge. Like you need somebody who has done this before, meaning you really can't do anything from scratch unless you have them.
I mean, it's just a lot of this goes into the issue that building anything is hard, right? Building anything physical is hard. There's just a lot of knowledge that goes into like, it's one thing to say for mechanical device, you can just do blueprints for whatever, right? You can just draw this, and it's just like in German there's a saying, Papier ist geduldig, paper is patient, right? So like you can put anything you want onto paper, right? And then you actually want to manufacture the thing and put it together, and you realize like you need to mount this thing on top of this thing, but this is after you've installed this subassembly, and now the part where you need to put the screws in, you don't have access to them, and this doesn't actually work, right? That's the kind of thing that happens with like whenever you're mentioning anything physical, right? There's just issues of this level of like just purely like at some points you're interacting with the real world, and there's just physics and actual hard constraints that you can't discuss your way out of. And that's the part where you need the experience of just like, oh, and it's not something like if you have this sub-assembly design in a way where it's like, this is all cool. Like if you could magically spawn it like fully assembled, it would be fine. But it's just physically impossible to just put this together if everything is not already there. Then you don't have something you can actually manufacture. And that is the kind of thing you hit everywhere, right? It doesn't need to just be something that is a beautiful idea and like a nice execution. There's all kinds of things that just go into like, oh, you need to be able to build this thing. If you do a chip, like every chip, like since the 80s, uses a thing called design for test. Because the thing is, this thing comes off a fabrication line, it might have random fabrication defects. Like if you whip out an electron microscope and spend like hours poring over that, you might even find out where that is. Like if you know there is one to search for and you have an idea of where to look. But these things are giant. Like, so how do you even find anything? The answer is like these things are like any chip, absolutely everything has a bunch of debug functionality just built into it. And it is a circuit, right? You can't like, this is not scaffolding you can add after the fact, right? If you want to be able to see what's in this register, there needs to be, in some way, there needs to be a wire from the bits in that register to somewhere in the outside world that you can probe, or you will never be able to find out what is in that register. So the way it works out, and this is wild, but this is like how every chip is designed. There's a thing called boundary scan. Basically, every piece of like storage, data storage, flip-flop in the entire chip, they're all daisy chained into one giant shift register usually, or sometimes multiple. Like this thing, like this bit of storage, like if you were in that scan mode, shifts its bit into the next bit of storage, which shifts its bit onwards and so on. At the very end, there's just a single serial port where like one bit comes out. And through the entire chip, there's just a daisy chain of like all memory, every single bit in that chip, right? It's just being shifted one bit along that scan chain, and like one bit pops out. And you can also shift in one bit in. So what you do for testing is you have these test patterns where you shift in a long sequence of bits to put it, like you can shift in one bit at a time. And like you do that often enough, like a couple million times, depending on how many bits, maybe tens of millions, maybe hundreds of millions of times. It's like, takes a while. And then you have it programmed to the state you want. And then you pulse the clock once, and then you shift out the state everywhere.
Oh, wow.
And now you see like what the entire...
Oh, wow.
So that's how you can debug these in principle. Now, of course, for testing, that is way too slow. So what you actually do is you just have this, like, there's a reset pin that's supposed to reset everything to 0. Like, that's something every device has. So you reset this thing, and you just alternate, shift in one bit, toggle, shift in one bit, toggle, shift in one bit, toggle, and see what comes out. And this was initially garbage and so on, but you can just figure out what the test pattern is that within the shortest amount of time gives you pretty good evidence that this chip probably works. Or maybe some of it doesn't work, but you can figure out what parts doesn't work and just turn off some of them via fuses and so on. Because that's another thing, like any chip that has like, if you look at a die shot of a chip, like there's all these regular grid looking things, and it's all memory. That's how memory banks look, because all SRAM. So any modern chip, honestly, is mostly SRAM with a bit of stuff that actually does computation on the side. Not quite, but that's what it feels like. It's mostly SRAM for real. And the thing is, these SRAMs are very regular structures. So what you actually do is like every time you put in a big piece of SRAM, because you have manufacturing defects. Any of these might get corrupted due to like whatever, random dust particle or something, right? So whenever you put memory, you just put 5 or 10% more than you need. And some fuses so that you can say like, oh, if this memory bank is bad, route to this memory bank instead. And then you sometimes, you see these scandals where GPUs, like NVIDIA is selling these GPUs and some of them are like 5% slower at blah, blah, blah. Because they have this at different scale. We're like, oh, like this can go to this texture sampler or this texture sampler. And some of them are good and sometimes they're bad and need to use the backup routing. And like 2 shader cores go to the same texture sampler. And then that both of these shader cores that share the same texture sampler now have lower throughput or stuff like that. But like everything is just designed in a way like, yeah, you build a bit more than you need and have some fuses that you can blow at manufacturing time to tell, oh, this isn't quite 100%. So we put this into a slightly lower bargain bin. Like whatever, you have these dies have 8 CPUs on them. We have the unit that actually sells 8 CPUs. So these all 8 need to work. But some fraction of them, 1 or 2 of them is busted. That's fine. We also sell a 6-core variant. And if you open the 6-core variant, it's an 8-core CPU in there.
Ooh.
It's just like 2 of them are disabled. Like waste not, want not. That's how that works. And the same thing, like it turns out just due to manufacturing variation, like some of these are just better than others in like more subtle ways. They're not completely busted. It's just like some of these are stable up to like whatever, 5.2 gigahertz. And some of them are only stable up to 5 gigahertz. But that's fine because you have versions of the chip you sell that you can clock higher, that are like the high-end versions. And these are just literally like the slightly better ones. And sometimes they even like, you've figured out some quota, like some percentage of these you sell as the like high-end ones, some percentage you sell as the low-end ones. Sometimes even some of the low-end ones are just as good. And if they're overclockable, you can clock them and they work just fine. Others don't, and you don't know. Yeah. But like this whole thing, like every part of this is just like, no, there's just variation at every step, right? It's not like a thing where it's like, we like to think of digital hardware as like, oh, it's ones and zeros. And it's like, no, at the low level, like it's like voltages and currents, and some of them are better than others. Some of them are slightly better than others. Some of them are slightly more stable. Some get hotter. Some get less hot.
Yeah.
it just
Yeah, but then
depends.
for like pricing and marketing, you want it's really cool that this is like adapted strategy for what is the physical reality, the underlying thing,
Yeah.
right? Like you adapted how you sell it, and you don't build like 7 different models for it. You build one, but it just accounts
Yes.
for all the manufacturing problems that might come up. That's really cool.
You built a few, yeah, and like I mean, like in the original AMD Zen, that was when the company was not doing well, and they were literally just doing the one thing. They built everything out of that. They had this one die called Zeppelin, and like that had just all the wiring, so you could put 4 of them next to each other to make the really really beefy like AFAIK server CPUs that used all the links that they had. Like the wiring is always in every single one of them to be able to connect it to up to 3 other CPUs. And like sometimes they're used, sometimes they're not. But they just did the one die. Like if you get like an early generation Zen 1 CPU, it just has 1 of them, and maybe the higher end versions have 2 of them, and the AFAIKs have 4 of them. And like some of them use the connectivity, some don't, but it's all the same die. And like some of these use like dies where like every 8 cores need to work. Some of them use dies where only 6 cores need to work, and those are cheaper, and so forth. And that's also like in the early 2000s, like we had Pentium 2s when we're working on FR08. And you could get the good, quote unquote, 400 megahertz Pentium 2s, or you could get the much cheaper Celerons. And the main difference was that the Celerons at the time were the same CPU. They just had half the L2 cache disabled. Because of this manufacturing variation thing, like some of them just had defects in the L2 cache that meant like, they can't actually have the full, I think, 256K or whatever it was enabled because it actually physically doesn't work. But some of them, like some of the ones that sold Accelerants, like had the entire L2 cache working just fine. And it turned out at that time, it was essentially just something like, I think it was something like a dip switch or something, or a jumper that he could just change on the CPU module on a Celeron, because they didn't bother. So you could just buy the Celeron, flip that switch, check if it worked.
Maybe it worked.
And if it worked, you just got a Pentium 2 400 megahertz at half the price.
You got the upgrade.
These days they've gotten like they're now doing these things with actual eFuses that are actually blown. Like this is like a one-way thing. You cannot turn them back on because people started doing this. But this is just a thing, just purely market like price differentiation, where they realize like, okay, we have these like to make our margins. We want to sell them at this price for the full size Pentium 2, 400 megahertz. And realize some people will not buy it at that price. And we're willing to do some work to offer like some product for that market segment that can't afford the whole price, but we don't want to ruin our margins for the entire product line. So we give them a cheaper version of this chip, but make it worse in a way that is easy for us to do at fabrication time.
It's weird though. Imagine this like
If
in a different
you-
field. It sounds so weird. You produce something that would work.
The thing is,
but
you
kind of damage
don't
it.
have to imagine that in a different field. That is how it actually works everywhere.
Is it?
It is. Like cars do the same kind of thing. Like for example, like if you look like a lot of engine tuning things, like in a serious car, like you have like the different versions of like, whatever, like this thing has like 20% more horsepower and whatever. And you go there to the retailer, like they own the garage, and like, I want the higher engine option, and they know shit, go in there with a laptop, like literally unlock things, basically put in a firmware update, like, okay, got 20 more horsepower, ta-da. That has been a thing for a long time. It's called chip tuning. So like this is literally the same engine, and they're just like, it's a couple $1,000 to get the firmware update that unlocks the higher capabilities. And it's just like, the thing can do this. They're not actually building a thing. There are engine options that are better, for sure, in a car. But like, this is everywhere. Of course, like, and it's also not just in the software context. I mean, software has been, of course, a multiplier for this. Same with like Teslas, where like, they had the whole ludicrous speed thing, like for the Tesla Model S or whatever, which turns out also just an over-the-air firmware update. Which means that every Model S they ever sold can do this. But the ones that have this enabled like are like, I think were like at the time like 10K extra or something. And it's like, yeah, you're paying 10K for a software update. But it's also not just things like this. You have like you have this in other domains as well, like where like certain upgrades are just like, yeah, we just go there, basically circuit breaker, tweak this thing, it's on, ta-da.
With the idea.
Especially things with maintenance contracts. In a purely mechanical device, you don't see this as often, purely because in anything that is a mechanical device, parts you don't use still cost a lot, right? You need to physically manufacture them. You need to maintain them. They might cause the mechanism to lock up, even if they're not actively used. Like they might cause problems. So don't see this as much in like stuff like that's purely mechanical. For anything electric, like it's not just computers. It's been this way for a long time.
Okay, Fabian, judging by the average time we spent on a single topic, we had at most one topic. So you will look at our list of topics and you'll see what have we actually discussed from the list. What have missed.
I warned you.
Let's say that we can do a round 2 or round 3 episode at some point in the future. But I want to switch like very drastically and talk about something that I've never talked about extensively on the podcast with people. Okay. But I found somewhere, either on your blog or in an interview, that you like point and click adventure games.
Sort of, yeah.
Is it true?
Like a lot. Like I used to like them. I mean, I just played them a lot in the 90s. I've not played them that much since.
Because
it was just.
Do you know that there are like, that's very niche type of games, genre of the games, of course. Yes. But there are a couple of game developers that are doing point and click adventure games today that are quite like.
Yes.
Have you tried them?
Yes. A few, but nothing very recent. No. I know actually like one of them. I don't know if they're still around. Daedalic, because they're in Hamburg. So at the time, I was at 49 Games, which was in Hamburg. Like what's the name? Like I need to actually Google this. Daedalic Entertainment is, not was. That's good. Yeah, Edna and Harvey and The Whispered World and Deponia. Yeah, that stuff. So that was going on while I was in Hamburg. And they were, of course, also part of the Hamburg game development scene. And some of the people from there would sometimes hang at the same bar that we used to go. Okay. So I know some of those people. But I haven't actually played those games either. That was after that time. I played the genre a lot in the mid-90s when it was, I guess, its heyday.
This was the peak of the popularity, right? Okay.
Yeah, pretty much. That was when you had like all the like early to mid-90s, you had the whole wave of LucasArts games, which were generally the best ones. You had the Sierra games, which had some of which I liked, some of which I didn't. Like they had a lot of like Sierra had a lot of this mean-spirited haha gotcha kind of thing that was just kind of exhausting.
The King's Quest, Space Quests kind of games.
Yeah. I think the best Sierra game from that era was probably Gabriel Knight, which still had some of these gotcha moments, but was nowhere near as bad as the others about this kind of stuff. Sierra just had a thing they would do a lot where like, oh, like you could have like in the climax of the game, like, oh yeah, this is actually not solvable unless you got this random item like 2 acts ago.
Yeah.
And so like you would discover like, oh yeah, this is like, I got to this point and like I actually can't win now because there's this random thing, and it wouldn't tell you like you need this thing. You're just in a state that's not solvable and you think you're stupid. And like you must be missing something, and you're not missing something. You missed something like 8 hours of playtime ago, and now it's just impossible to win. And this like I don't know, didn't
8
feel
hours
good.
of playtime or like 2 weeks ago, because it's and it was rough because like the game wouldn't tell you, it would tell you nothing.
Yeah, it's the same. Like if you have like if you look at like tabletop role playing games, like the original stuff, like original D&D was also like, it came from the whole wargaming kind of thing, like Warhammer kind of style games. Warhammer itself didn't exist then, but that kind of game, like it's like big, like strategy on a table and whatever. And like, if you look at like some of the early D&D stuff, it was very much like, oh, it's a dungeon and there's just traps everywhere, and you make one wrong move and you die, and it feels very antagonistic and mean-spirited, which luckily that genre has kind of moved away from. When like the Sierra games felt in a similar vein, where it's just like, oh, like a lot of it is just basically things that are padding, like, oh, like we gotta do a maze, which even like a lot of the LucasArts games did early on. It's just like, yeah, have you just go through a random maze, and like that's an extra half hour of playtime where you need to map this out and so on. It's just not quality time. It's just it's filler. And like the Sierra thing of like, haha, I got you. It's like, cool, great. Like, you're just wasting my time now.
Yeah, the smiling skulls when you were dead and you needed to replay. Like, this is such, or like a random quote that would like sort of make fun of you. This was very strange. Strange aesthetic choice.
Yes, it just felt mean spirited. I don't know.
So what games do you play now then?
Now mostly, I guess there's still some sort of like point and click-y things that I sometimes do. Like I've been like playing a bunch of Dispatch lately, which is sort of like Telltale, sort of like, that's not even point and click. That it has like Dispatch has like a story mode kind of thing, which is more like interactive movie style with like a handful of choices. But like there's this mini game in there where you just actually like, the genre of Dispatch is like superhero workplace comedy. I don't know. And there's a mini game in there where you actually have to like dispatch superheroes to handle incidents, which like I've been playing a bit with, like trying to like min-max that, because that's just a fun problem. It's constrained enough that you can try to figure out an actual optimal solution, which is just kind of catnip for me. There's lots of like puzzle games that I like various kinds. And the genre I tend to actually spend most time into is just sort of narrative heavy RPGs.
Baldur's Gate?
Like Baldur's Gate I spent a lot of time on. I still haven't completed my playthrough of that yet, because I just at some point got sidetracked and I just basically forgot where I was because I hadn't played it. Like that was a thing like 2 years ago. Early December of 2023, I twisted my ankle really badly. And I was just like, started playing that game because I like also like couldn't really do anything else. Like that was just while jogging. I was like, okay, I'm basically grounded for the next couple weeks.
Wait, but Baldur's Gate 3? It was out?
I think that was 2023, or was it was it 2024? It would have been 2023, I think.
Oh, yeah, 2023. Okay, August. Okay.
Yeah. So like that was when I really got into Baldur's Gate 3. But then, like, because it was early December, and then since I live in the US and all my family is in Germany, what I do is like basically like every year for Christmas I go visit my family, and while I'm in Germany also visit my friends. So it's usually a 2 or 3 week thing. So mid-December, like after playing like Baldur's Gate a lot for like 10 days straight, I on my home PC, not on my laptop, which like it didn't even have a fancy GPU at the time, so I couldn't really play it on there. Then I went visit my family and friends for like 3 weeks. Yeah. I was like, oh shit, I don't remember anything about where I was. And then I've been playing it a bit since, but like it's just hard with a game like that where like a lot of narrative strings are going on, and you're just in the middle of some random quest, and you come back like 4 weeks later, it's like, oh fuck. And I literally like I'm somewhere in Act 1 still, and I literally like I'm in a space. This is where like this weird golem enemy is, whatever, something like that. And I'm literally in a space there where like I don't know how I got in there, and I don't know how to get out. There is a basically boss fight that I can do, except I can't because like I am woefully under leveled to attempt that much I can tell you. and I just can't get it. It's like I'm just basically stuck there, and I don't know what to do. And I would need I could just look up how to do that or find my way out. But that's when I kind of bounced off that particular one. I need to pick it up again at some point. I did spend a lot of time when they came out, which is now long ago, on the various Mass Effects, which I really enjoyed. I did play through The Outer Worlds when that came out. Did some Cyberpunk 2077, but that was a bit too grimdark for me. And Outer Worlds 2, I have a started playthrough, but that's I started that last week, and I'm not very far. I'm somewhere in Act 1. I don't know. So ask me how I feel about that game once I've done a bit more, but I'm still in the starting area.
What about puzzle games?
Depends. I'm really, really into the whole Zectronic games, but not all of them. Not all of them. Some of them I really like. I think Opus Magnum is probably my favorite. And some of them I'm just kind of for example, Space Cam I never really got into. There's the ones that have hardware-y or programming-y things, which some of them I really, really love, and some of them I'm kind of lukewarm about. But in general, that's a genre I tend to enjoy. I've tried Factorio, which is supposedly life-ruining. I've now tried it several times, and I've never even made it through the tutorial.
You didn't have
I don't know what it. I would it's not that I'm opposed to the idea. It's just that something about I don't know, every input I do in that game, you have walking around, but it feels like this game is intentionally trying to mess with me. I don't know, nothing in that game works the way I want it to work from the input side. I've just bounced off it hard several times. Something about the controls. I can't put my finger on what exactly it is, but it just feels yeah. And it's just this is I try to play it, and I'm playing basically through the tutorial part. And there's in this thing, there's the first tutorial where you actually have these aliens attacking, and you need to set up the machine to be able to get munitions to fight them off. And with them trying to attack me, once they start doing that, I cannot manage to get the production line up to a point in time where it actually produces ammunition fast enough for me to continue fighting them off, and then I just die. That's how far I got into Factorio, which is maybe 1 or 2 hours of gameplay into the tutorial. It's I don't know, man. I don't think this is for me. And so I've not gotten into any of the interesting parts. No drones, no blueprints, nothing. Just very, very early on, basically you handcrafting, and I'm already I don't know if this is for me.
But if you are into narrative RPGs and puzzle games, are you also in this a subset of narrative puzzle games like Obra Dinn, Outer Wilds?
Oh yes, absolutely yes. I played Obra Dinn. I really, really enjoyed. Curse of the Golden Idol and Return of the Golden Idol. I've inhaled.
There are 4 DLCs for the Rise of the Golden Idol.
Yes, and I've played through all
nice.
of them. It's a bit weird. The last one is a bit weird because it's just complete change of scene and pace.
The pirate one.
Yeah. Which is the actual Golden Idol doesn't even play into that one. Or not really. Sort of. It's fun. I just feel the positioning, I don't know. It feels like they should have probably swapped the 3rd and the 4th DLC. So the pirate one that's as a breather, and then do the one that's in Ancient Lemuria, which feels sort of the climactic one where get the big picture of how this all works. I don't know.
Okay. Nice. We have a lot of topics on the list, but I think because we're 3 hours in, that's a good place to stop. This was a huge computer history lesson. And the latter half, and couple of questions about your programming weird projects a long time ago. We can do an episode episode number 2 in the future where we get to the more modern stuff as well. But
Sure.
this was awesome. This was awesome. I had no idea about the lineage stuff that you mentioned, and it was really nice to learn about it. And like you have the crazy ability to remember all the letters and numbers and like versions and then like connect them all and just like to pull this up from memory. This is wild. And your blog is like incredibly detailed. If anybody who is interested in like serious technical knowledge, can you spell out your can you bring up the name, the URL for the blog?
Yeah, that's Giesen, FGIESEN.wordpress.com.
Yeah. You have
which is my name.
Incredibly detailed blog posts. They're wild.
Thank you.
Nice. Fabian, thank you so much for joining me.
Sure. All right. Yeah, thanks for having me.